usted exactamente es es uno de los mejores y los grandes universidades de geología en el mundo. Bueno, gracias a todos por venir y ya, te presento Zhaoshan Chang. Buenos días. Thank you, James, for the introduction. And Xinjiang and I, we very much appreciate the opportunity to be able to visit the Skarns. It's one of the largest skarn deposits in the world. And so we'll talk about skarn deposits and skarn and related deposits. Some of them are skarn deposits, some of them may also other types of deposits. Okay, and we'll say why we care about skarn. Obviously, you guys know already, and we're mining a skarn deposit, but also outside of the Skarns, and there are also many skarn in the world. So I have a database, and that's only getting the data from the public literature, and that's already more than 1,700 skarns. And that's the distribution of the skarns in the world. And the situation is, as long as you have limestone wall rocks, and if you have a little bit of oozy magma, and then very likely you will have some skarns. Some of them are big, some of them are small. And the situation becomes so common that sometimes I get emails or calls from friends say, I'm doing exploration, I'm trying to find a porphyry deposit in Papua New Guinea in the jungles or in the high Andes. But I see skarns. What do I do with the skarns? How can I use the skarns to find porphyry? So sometimes you may encounter a skarn no matter where you are looking for it or not.
¿Hay algunas preguntas?
Okay, I will continue. And in terms of the economic values, skarns is the major source of tungsten and tin. And it used to be the load pressure is low, and it doesn't mean much. But nowadays, tungsten and tin become critical minerals. They become more important. So we are getting it here. And it's the number one source for tungsten and tin. It is also an important source for gold, copper, zinc, lead, silver, moly, and iron. And this is example. This is Antamina, and that's back in 2014. The pit is already very big, and at that time there was about 3 billion tons of resources. Copper and zinc and silver and moly. So that was 8 years ago, and so now it would have been much bigger. The only thing is they only report the remaining resources. They don't report the total resources. Okay, in addition to those ones, those are most common ones. We also have minor or byproduct of boron, beryllium, bismuth, cadmium, cobalt, germanium, gallium, germanium, indium, etc., rare earths, and even uranium. So you will notice that many of those elements nowadays are in the critical minerals list. Some of them are very important for, say, we have the big flat screen here. We have to use indium to make those flat screen and your laptop screens. So those metals actually are becoming more important.
I have a question, Zhaoshan. Are there any particular skarn type of deposits that are more rich in the rare earth elements and more rich in strategic elements?
It depends on the Many of them actually zinc skarns. The one related to tin actually turns to have more indium. Not every indium is a byproduct of tin skarns. This one is in the sphalerite. Yeah. In the early days, the companies are sending the smelter, sending the zinc concentrate to the smelter. They didn't know actually the smelter was secretly extracting indium out of it. Yeah, indium and germanium, they are out of sphalerite. And those rare earths turns to be related to the more felsic and especially alkalic magma, and uranium also. So China had uranium skarn, all sorts of minerals, and rare earths also, very fractionated magma. And in addition to metals, actually they also produce industry minerals. So jade actually is a gemstone. So in Asia, jade is a big thing. So it sells for more expensive than gold. And molassanite and fluorite, some of the big quartz crystals and dioxide, like the perchlene, they can also have special usage. And so they also mine for those things. Okay, so that's the economic value of skarn deposits. And also, as we mentioned, skarns may have a close relationship with porphyry deposits. And this is Erzberg, Grasberg district, combined copper and gold combined together. This is believed to be the largest one in the world, Indonesia. And our industry always have trends. In certain years, VMS deposit is very popular. Everyone wants to look for VMS deposits. And in the past 3 decades, probably everyone wants to look for porphyry deposit. And everybody is saying Erzberg, Grasberg is a porphyry district. But actually, when you look at the detailed resources, Clyde Lice in 2012, he published a paper. He split the skarn resources and porphyry resources and skarn resources. It turns out that skarn is about 2.8 billion tons and porphyry about 2.3 billion tons. So in terms of the metal, it's about 55 of the copper is in skarns and 45 is in the gold is skarn. So roughly half. 50-50 for Erzberg, Grasberg district. Other deposits, Oktedi in Papua New Guinea, that's another big one. And this one is 80% skarn, 20% pulp. And Bingham is a very big one in Utah. This one is 20% skarn, 80% the skarn system everywhere. There are many other examples in terms of the skarn and porphyry connections. So sometimes for the public relationship, you want to release to the market, and you may want to say, I have a porphyry deposit, but you still can use skarn deposits to look for, help you to find more porphyry deposits using the Lumi. Okay, that's another important thing. And also, if you find a skarn and you figure out which part of the skarn is proximal, which part of them is distal, then the proximal part you can move for the porphyry center or the intrusive center. Depends on the features of igneous rock. You can get a porphyry deposit. You can also, it's another possibility, you get resin deposit inside the intrusion. This one typically related to tin mineralization. And from the distal part, if you know your distal part, you go further out, you can have CRD deposits. And the CRD deposit is mostly zinc, lead, silver, sometimes manganese. And from the CRD deposit, you go further up, you can have kaolin deposits if you are in Nevada. If you are outside of Nevada, everything looks very similar, and you can only for kaolin-like deposits because the kaolin people will not recognize the deposit outside of kaolin as kaolin deposit. A subtle difference is kaolin deposit in Nevada, all the gold is invisible. They are in the lattice of pyramid. Outside of Nevada, you still have the silicification of the limestone. The alteration is similar. It's just growing. And James worked at Japan. He had a lot of experience on those type of deposits in Japan. And also in China, there's two triangle districts in China, northwest and southwest. So also a lot of those kaolin-like deposits. Okay, that's more distal. Another direction is this is the host rock. They are still in carbonates. You have those kaolin-like deposits. But if you change your host rock into volcanic rocks, and on top of your limestone stratigraphy, you have volcanic rocks on top, or sometimes it's igneous rock or intrusive rock. Actually, those CRD deposits, those veins will transition into the volcanic rock, become epithermal deposits. Like in La Colorada in Mexico, and that's porphyry in the bottom, then skarn, then you go shallower, you get CRD deposits, and then on top of that, it's volcanic rocks. And the vein just going into the volcanic rocks. And if you don't know there are skarns down below, you just look at the veins. It's sphalerite, galena, quartz, calcite, and this is typical assemblage for intermediate sulfidation epithermal veins. Yeah, so we are transitioning.
Pero bien, no hay preguntas. Claro. ¿Es posible to form epithermal deposits in sedimentary rock?
It is possible, and you can have intermediate sulfidation, low sulfidation in sandstones. In that case, you are not looking at major veins. Volcanic rocks, the epithermal mostly have veins. But in sandstones, there's deposit in China, in sandstones, they don't have many veins. That's because the permeability is high, porosity is high. And they just have newer quartz cementing the going into the pore space in the sandstone. And with some technologies, you can actually see there's new grooves of quartz together with the gold over the critical quartz group. There are also high sulfidation deposits, epithermal deposit in sandstones. But on the Nordic in Peru actually is more than half of the resources are in sandstones in Emu formation. Yeah. Good.
So yesterday we saw a sample from a silicified sandstone with some scans, but it was very silicified. Could that be, and maybe the Brodolith was a fairly porous sandstone? Could that possibly be similar to what you're talking about, that that's actual epithermal style alteration?
Yeah, that one, in that case, if you are close to the sandstone, at the beginning they have sandstone, but in the thermomorphic stage, they may be converted to quartzite. So their permeability actually becomes very low after that. Around Bingham, there are limestones and sandstones, but close to the intrusion, they become quartzite. The local people core everything quartzite, but actually if you get away from the intrusion, it's still sandstone. And then the situation is if you are in an epithermal environment, the temperature is not high enough to convert that to quartzite. On the other hand, if you are close to the intrusion, the early stage, metamorphic stage, you turn that to cortex. And then when the water is released out of the magma chamber, it's typically explosive. So lots of energy related to the water release. Then you break up the cortex, and that gives you the space to form the mineralization over in other happen? Yeah. And you also notice the minerals actually showing different temperature. The low temperature ones typically sphalerite galena, they form a relatively low temperature. And at Azohaka, it's a hematite and partially changed to magnetite. And those ones' temperature is higher than the sulfides. When you see that, you're probably closer to the intrusion. And how close it is close, and later on I will show the geometry of all skarns, then we can talk about the distance, roughly. Okay, then obviously in Peru, it's a country also very rich in skarn systems. This is the recent compilation. There are 42 skarn systems. Some of them are purely skarns. Some of them are CRDs only. Some of them are porphyry and skarn together. And and obviously you will know Las Bambas is here. That's Las Bambas. It's in an area with lots of skarn systems. And you go north, they continuously to have skarn or skarn porphyry system and or CRD system all the way to Anchorage next to Catamacan. Then another big one is Lumina, number one here. After I finish that and already noted that probably 3 or 4 current deposits I need to add into this system, into the database. Peru is a very rich country in skarn porphyry and CRD system. Okay, now we have talked about the importance of skarns. Let's look at the definition of skarns. The definition of skarns actually is simple. It's mostly not related to the genesis. It only depends on the mineralogy. So as long as you have calcium-rich garnet and or actually I could add and and or wollastonite. So if you have wollastonite, some of the skarns, their mine wollastonite, they only have that. Okay. And so we have to say it's calcium rich because there's another type of rock also have mostly garnet heritage. You guys have any guess of what other rock have garnet heritage? A lot of garnet heritage. Metamorphic will be eclectic. Those ones are high pressure metamorphic rock. And the only thing is they are not calcium rich. The garnet species mostly is high, and the heritage is not. Some people will say the skarns to have us to core the skarn deposit, you have to have limestone or you have to have intrusion. Actually, that's not exactly right. The type locality of skarn, this term came out of Sweden, and at that type of locality, there is no limestone, there is no intrusion, just massive skarn. Brown skarns. Yeah, so that's related to metamorphic plasma fluid. It is true that the contact between the intrusions and the carbonates is the most favorable location, but it's not the only location. Okay, Next, we will see there are several misconceptions about skarns. There are some people call skarns contact metamorphic. Well, contact metamorphic will give you some industrial minerals, but will never give you the metals. So this one, we will say 90%, this concept is wrong. It's not a metamorphic. There is a proportion of metamorphic skarn there, but it's not typically not the economic one. So we need the hydrothermal activity on top of the metamorphic process. Another concept is say, oh, you said contact metamorphic is not right. How about contact metasomatic? Many people query contact metasomatic. Yeah, this one, many of the skarns occur at the contact zone is also metasomatic. On the other hand, this doesn't give you the full picture. Some of the there are also large amount of skarns are fairly away from the contact of the intrusions. You can have distal zinc, lead, silver mineralization, or sometimes you can have tungsten and moly and copper. They can also be distal and along certain veins, structures in certain locations, and up to 4.5 kilometers away from the property. Okay, so this one doesn't give you a complete picture of it. Another type of thinking is I need to look for the limestone. If I don't have limestone, I can't avoid skarn. This is again there's small proportion of skarns actually is not related to limestone. Skarns may replace igneous rocks. Some of them, like gold skarn, like in Tongan, in Ivory Coast, that's a country in Western Africa. And over there, this one is about 4 million ounces of gold, about 3.5 grams. I agree. And this one is totally hosted in basaltic andesite, so it doesn't have carbonate at all. Another one is Nimbeca in Ecuador. There's also in South America, that's also a deposit of gold deposit, replacing animals. Some tin skarns in there's several of them listed here. They're in northeast Queensland. Those are skarn deposits, and they are not related to. They don't have limestone around. They replace dolomite, which is maybe equivalent of diabase, right? In Australia, UK, right? Oh, so that's that. And also there are iron skarns in Western British Columbia and in England, and also in China, several of them. They are again replacing the double. So matrix lines. So again, keep an open mind. Some of the skarns may not be replacing directly limestone. They can also be some.
Yeah, there's no example of the copper deposit or the skarn replace years works.
Not yet. Well, you can Candelaria in Chile, and if you go there, there's this is copper gold. The limestone above and below that is mostly basaltic andesite and basaltic rocks. And some of around the Candelaria, in the Candelaria district, there's actually the main deposit is Candelaria, but there are also other deposits. South of Candelaria, southwest of Candelaria, the deposits are purely because they are replacing the limestone above it. And in Candelaria itself, it's replacing mostly the salty rock. And there's most of the alteration mineral at the current day is amphibole. And But if you look in detail and the microscope, there's actually a little bit of residual earthy there. So the traditional thinking here in South America is saying taking that as an LCD deposit. But if you really look at the mineralogy, this is actually, oh, I don't want to argue with somebody, but if you brought up the question, so I make a comment. That's the example of gold. So that's the definition because skarns are defined by mineralogy. So we'll look at more details about the minerals. So here I'm listing the major groups of minerals. So we can have a group of many species of garnet and several species of hurricane. If your rock is dolostone, you can get olivine. And we can also have hurricanoid. Hurricanoid, you probably are not familiar with this term, but you probably are more familiar with wollastonite. So wollastonite is one type of hurricanoid, and rhodonite is another one. Zinc-like deposits. And epidote is another group. Amphibole is common. Mica is common. Also, carbonate, you can have siderite, anthrite, and rhodochrosite, different species, and other. In terms of mineralogy, is one of the deposit type with the very rich species. And for now, we're only looking at the major ones. And major mineral. Okay, because garnet is the definitive mineral, so we'll spend more time on garnet. You are already familiar with this because you know there's grassular garnet and andesite garnet. And you see here at the A site, the common formula is A site, B site, C site, and oxygen. It may be looks like many species. It's not that complicated. The C site is always silicon, so simple. And the A site for skarns is mostly caustic, so nothing changes. The only thing changing is at the B site. So if it is aluminum end member, then it's grassular. And if the end member, that's a andesite, name. And so together, some people also call it groundite. Groundite is basically taking the GR from grassular and AND from the andesite. Okay, so that's the mineral we can see. Actually, in the field, when we see mineralogy, we also need to think about other conditions it may represent. So if we have a look at the iron here, so in nature, iron occur typically in two species. So iron 2+, iron 2+, and 3+. So when you have an element have different cations or different properties, then you can look at this and think about redox rate. And so whether it's reduced species or oxide species. So now, if we look at the garnet here, we have the iron here. What do you think about the iron here? Is this 2+, 3+? Yeah, we look at the B side, it's 3+. 3+. Is this reduced or oxide? Oxide, okay? Because the reduced species is iron 2+, and so 2+ is reduced and 3+ is oxide. And this one is oxide, this is more oxide condition. So after you recognize garnet, also think about the condition. Okay, and so that's the most common garnet species in skarns. Sometimes we are here in relatively younger terrains and not so much metamorphic, regional metamorphic. There's still some, but not very strong. You go to Australia, there are places with very strongly metamorphosed protozolic rock, and then you start to have other species of garnet. And this time, the B site is not changing. They're fixed as aluminum. And now what's changing is at the A site. If you have manganese, and that's for specialty. And if you have iron, this is almandine. And the pyro is magnesium rich. Okay, and so sometimes you see all those garnet shapes, the little garnet in the shapes. Those ones are typically almandine, iron rich. They may also contain a small amount of manganese, so that's a specialty component in that. So that's typically in metamorphic terrains. But when you have marble lenses in those metamorphic rocks, and that marble lenses may be also converted to skarns, and some of them will be rich in those kind of species. And those ones we also call it, because it contains less calcic, so we call it subcalcic garnet. We don't have it here in Las Bambas. And actually in South America, it's very rare. In some other countries, it's possible. Okay, as redox label already mentioned. So that's garnet. Another group of mineral is pyroxene. So pyroxene also A site, B site, and C site. The C site is always silica, so it's simple. And the A site is always calcium, that's also simple. The only thing changes is at the B site. So if it is magnesium rich or magnesium end member, that's for the outside. And if there is an end member, it's anorganic. And if you change to manganese end member, or tanzanite. The most common one is between iron and magnesium. So some people also call it phthalate. You don't need to call it. Just in case you read papers or read report, some people call phthalate, you know actually it's a solid solution of pyroxene. Okay, and those minerals actually are relatively easier to tell in the field. The outside is very light green color, and when you have more and more iron inside the pyroxene, the color gets more and more darker green. So tanzanite will be darker green, dark green. The tanzanite is actually starting to look brownish. When you change from green color to brown color, and it's more manganese in it. So we change to brown and eventually to end member tanzanite, very strong. Decent photos. Okay, so that's the accommodation. Another thing, again, once we recognize the needs, we want to think about the conditions in which those minerals form. So we see our friend again, here, iron again. Well, have a guess. What's the charge here? Is it 2+ or 3+? Yeah, it's B side, so it's 2+. Well, if it is 2+, it is oxidized or reduced. Reduced. Very good. Yeah. You guys will be more expert in Skarns at the end of this short course. Yeah. Very good. Very, very quick. So that's a reduced species. So we always say garnet pyroxene, garnet pyroxene, garnet pyroxene. But actually, they may mean different things, slightly different things. When you see garnet, you think about likely it's oxide condition, and you see lots of pyroxene, possibly reduced condition. So there are more complications, but the major thing is redox fluid control.
Oh, a quick question. So if you've got pyroxene, so let's say diopside.
Yeah.
Diopside Mg in that case is 2 plus.
Yeah. But MD in nature, it only has 2 plus. It doesn't have any other charges. So it's magnesium is not indicative. So the elements in nature, if they have multiple charges, they will show the redox. Yeah. So one example is iron here. Oh. So iron has this. And you guys think about another element that in nature they may occur in different charges, different redox states.
Carbon.
Carbon, yeah, carbon. Sulfide, yes, sulfur, very good. So carbon, we can have CO2, that's 4 plus, and we can have graphite, is carbon 0. Then we can have organic material. Those are mostly methane, and this one is 4 minus. They do show difference. And sulfur also, sulfur in pyrite is sulfur -1. In pyrrhotite is -2. And how about anhydride, gypsum? Those are 6 plus. Yeah, this much. So that's why when we see in the Bamba, Spire Bamba, the drill hole 006, we're in the drill quartet, and when you see those anhydride, that tell you that the system is very oxidized. Yeah. That's another thing. You look at that, lots of garnet telling you it's oxidized, and you have anhydride telling you it's oxidized. And you don't have any pyrrhotite, you don't have any arsenopyrite. So those ones are more reduced, and you don't have it means. So that's the thing. We look at mineral, we also think about the condition. Okay. Yes.
About the garnets, just as the subcalcific garnets, they contain calcium.
Yeah, subcalcific means it's less. So there's no calcium. Yeah. So there's no calcium at all. Sometimes we can have solid solution between granular and spiracetin. So that's less calcium. Next one, we're going to look at the carcinoid. This one is even simpler. So A side and B side. The B side is always silica. So it's always there. The only thing is the A side. So the A side change to here. If we have calcium, that's the most common one. We have wollastonite. Yeah, wollastonite is always white, and it's prismatic and typically form radio aggregates. And the hardness is between your steel needle and your copper needle. So steel needle cannot scratch it. You scratch the mineral, you get a yellow color. That's because the copper gets scratched on the mineral. And if you use your steel needle, actually you can scratch it. Yeah. So when you see that, that's wollastonite. And rhodonite has the same crystal habit. You have also prismatic and radio aggregates, but the color is dramatically different. This one is pink or purple color, rhodonite. And then in between the iron one is there's not common to have the end member and iron end member. That would be ferrocyanide. And typically you have the solid solution between manganese and iron, and that's permangite. Permangite is brown color. And another one is solid solution between rhodonite and wollastonite, and that's for blastomite, also brownish. Okay, so manganese somehow has a color of pink. So do you guys know manganese carbonate, the end member manganese carbonate? If we have manganese carbonate, very good, rhodochrosite, yeah, and rhodochrosite is pink also. Beautiful mineral. It's the state rock or state stone of Argentina, and also, well, the country stone of Argentina and the state stone of Colorado. Colorado actually produced very good rhodochrosite. Once I was passing the Buenos Aires airport and I was looking in the shop. I said, "Oh, this mirror is beautiful. I want to buy it." And I look at price, very expensive. They said, "This is our country stone. It got to be expensive." So that's Argentina and rhodochrosite. So remember the color link. And when manganese is carbonate is purple pink. When it's silicate, it's also purple and pink. And when you mix with others, you change the color to brown. Next, we'll have epidote. Epidote looks complicated. There are many elements, A side, B side, C side. But again, if you really look at that, it's not that complicated. The C side, again, it's always silicon, so no change. The A side is always calcium, again, no change. And the B side, you will see that always aluminum, always 2 aluminum here. The only thing changes is 1/3 of the B side. If it is an end member, that's epidote. And if it's aluminum end member, that's clinozoid side. Okay, those two actually also have a color difference. If it is iron-rich end member, it's this yellowish green, very distinctive. That's epidote. If the clinozoid side, actually you lose the green color. It's either slightly pinkish or actually it can be dramatically pinkish. Clinozoid. Again, if we see our friend again, iron P is here. Okay, what do you think? Is iron 2+ here or 3+ here? 3+, yeah, it's B side, so it's 3+. And this oxide are reduced. Oxide, very good. And see, when you see those, and you will know it's oxide condition. And there are other examples, like in watershed, it's a plankton skarn in Queensland, Australia, and over there, the epidote is clinozoid side. So that's actually a reduced system. There is no iron-rich garnet. The only over there is a solid solution between granular and sphagnum. No androtype. Again, that's consistent with the reduced system. Okay. And in the crochet, James and I were also discussing. So some places there's lots of epidote, but in the Stambas, in the Ferrobamba, beautiful, we look at only small amount of epidote. And why is that situation? And that's probably related to there also 2 aluminum here. If your limestone is pure, then there's no aluminum around. And then even you have iron 3+, but you don't have this, and so you can't make epidote. And the garnet will likely be more androlytic, and some of the Skarns system you can have more than 90%, 95% androlyte, even 99%. This is for it.
So it just translate something there. So aluminium, you can transport aluminium in hydrothermal fluids.
Very difficult.
Que no puede transportar aluminio. El aluminio viene de la si la roca tiene aluminio, porque dice pura no puede precipitar idiota. Solo si el protolito tiene alguno, roca líquida o posiblemente una lutita que dice sucia.
Do you notice, James, to follow up, do you notice more epidite in the shaly layers than
Well, no, at Fuerabamba we get very little anyway. But in South Africa, we're doing, and there's this whole scan category of epidite endos. And it's got really high aluminium, and then it's got high titanium, got high thorium, scandium. So obviously it's an endospan, but it's been so altered, it's altered. So now Alfonso been going through and reinterpreting and reclassifying it all now as an endospan.
So why wouldn't you get epitope in the shaly horizons of Fuerabamba at aluminum?
Yeah, that's right.
It's probably the proportion. If the shady ones, if it is dirty limestone, small amount of clay, you make those maybe 50% granular, 50% andesite. That tends to have aluminium. If you have too much shale, you actually become calcium hornfeld. Later on, we'll talk about that. And then that's the end of it. They can't be reactive anymore. You don't form, you garnet everything.
Algo importante que mencionaron en la discusión, tener presencia de biota, por lo general muchas veces la roca está muy alterada por el biota, y en algunos momentos se estuvo entendiendo que era un exoescarpe biota, pero en realidad el indicativo de presencia de biota nos está diciendo que el protolito es imposible que sea imposible. Entonces, tomar en consideración y muchas veces observando el detalle podemos identificar un poco la.
You're just mentioning the same thing that when there's strong epidote alteration, that it's typically the intrusive.
No es tan importante en Zhaoshan estamos mirando y hablando y plano. Este es importante. Epidote igual en los.
¿Es una regla?
Es una regla. Okay, no, pero los canon creen con los pocos y tener epidote en los pocos exos, menos que 5% todos los textos. So one thing though is we do get epidote, very beautiful radial aggregates, unified aggregates. In the core scan in Zhaoshan, in core pockets, only in this space. Not a lot, a few percent max. Sí, exacto. Y la textura está ahí muy fino. Si quiere, hemos estudiado este punto bastante un año en Cochabamba. Entonces, de los canales de tiroides. Y el resumen es masivo, es endo.
He's just confirming.
Yeah. Deposit by deposit, some deposits exist. But here, maybe the combination is just not right. Yeah, it has to be the endosperm.
So, she and I'm sorry, epidote in the exoskeleton.
We'll talk about that later. Okay, we'll move on to like other mineral. So another common mineral is amphibole. So amphibole again, quite complicated. But again, so this is the D site is always silicon. So simple, and then the B site is always calcium in skarns. If it is outside of skarns, this is not right. In skarns, we have lots of calcium, so the species occurs in skarns, they all have calcium, the B site. The A site is occasionally you may have sodium-rich ones. Not very common, but you do have some of the species. Then the changes is at the C site. So the C site is here. If it is magnesium end member, it's tremolite. And if it is iron end member, that's ferroactinolite. And so actinolite is very light green color, and ferroactinolite is dark green color. Again, similar to pyroxene, it's related to the iron content. The more iron you have, the darker color it gets. And typically what we see is the solid solution between the two end members, and that's the name actinolite. So actinolite is a solid solution between the tremolite and the ferroactinolite. So that's the most common species in skarns. Sometimes, again, if you go to the distal part and low temperature, we actually get manganese-rich one. And guess about the color. What would you expect the color to be? Pink. Pink and brown if it is small amount, and then it's brown to pink. I haven't seen the end member yet. I haven't seen the pink one, but I saw those brown ones. It's very, this manganese actinolite. Hornblende is start to have magnesium, is hornblende, and that you have to have magnesium around, aluminum around. And occasionally you can have the sodium one with lots of iron. See here, there's no magnesium, it's iron. And this one, Hastings site, occurs in Mount Lindsay, is Tinscar in Tasmania. So this one is very dark green. And so in the drill core, if they're not polished, you can barely see a little bit of green tint. It's almost black. And for teaching, I polished many of the rocks for students to see it better. But this one, I did it. I did the polishing, then it became black, and it had made it worse. It's a reverse example of Hastings site. So after polishing, it becomes black. It's so dark green, and because it's so iron rich. Okay, so we have those two are the most common ones. You may have other species.
Does that really mean though that the iron actinolite is reduced, indicating reduced conditions?
Yes, it is.
And so tremolite would be more oxidized, this more matrix. So
yeah, tremolite is magnesium, doesn't say anything. But if you have the actinolite green color, it is relatively reduced.
what do you think about the actinolite we saw in the drill core?
Yeah, there's fluctuation probably during the Skarns system, because otherwise we won't get the sulfides. The time when we form the sulfides, it's already a reduced condition. Because you start with sulfate and then eventually sulfide. Okay, and so that's the amphibole. Then there are other minerals, and it's listed here. And so vanillonite, you may or may not have vanillonite. Uvite is a mineral which is black and stubby. The shape of the mineral is like this kind of shape. It's not a rectangular. It's parallelogram, and it's stubby, and it looks black. It's semi-metallic, black color. And scapolite, we may also have scapolite. Scapolite is can be white, can be dark. So this one is harder than 5.5. This one is harder than 5.5, and also typically prismatic tube, big enough. You can see the prismatic shape. And scaphylite, this mineral, if it can occur in marble as a porphyroblasts. When you have evaporite in your limestone stratigraphy. So if there's gypsum and this one contains, remember, see this one contains sodium. So if you have evaporite in your limestone, you have the little supply of sodium chloride, and then you can have porphyroblasts of stuff. And in skarns, again, if there's highly saline in the early stage and maybe later stage also, you can also have scaphylite. Another one is a northite, which is a calcium-rich particles. Not very common, but if you do microprobe analysis of some of them, actually it turns out to be these calcium-rich particles. And again, sometimes if somebody say, oh, I have a northite and it's surrounded by limestones, have irregular shape. Or sometimes petrologists, they only recognize plagioclase. When you see plagioclase, they always think it's igneous rock. But actually in skarns, we can have a northite. Another two minerals here, watch out for this. K-feldspar and biotite. If you have been always working in the porphyry community and you always think, oh, I have potassic alteration, that must be potassic alteration because the two minerals are indicative of potassic alteration. If you are working in skarns, you have to think again. Those ones actually is low temperature in skarn system. And you kind of think of it, even in epithermal deposits, intermediate low sulfate epithermal deposits, you have a K-star in this. Yeah, very good. It's the name, just change a different name. It's called adularia. So adularia is actually orthoclase, pure and member of K-feldspar. Yeah. So K-feldspar is a solid solution between orthoclase and albite. And so adularia is the orthoclase element. So it's common K-feldspar can be low temperature. And in skarns, you see this from time to time, typically in small amount. But in El Toque in Chile, it's a zinc-lead skarn. And over there, locally, there's a lot of this K-feldspar. It's white color. You think, oh, this is white color, it may be calcite. Potassium doesn't follow. And you scratch it pretty hard, harder than 5.5. When you have that kind of situation, think about the possibility of K-feldspar. You say, why not quartz? Well, it's possible to be quartz. What's the color of quartz? Typically, it's translucent. And this one is just plain white. It's not translucent. We don't have that kind of white mineral, hard, and it's not translucent or transparent. And then think about the possibility. Okay, another one is biotite. So biotite is probably in skarns. Phlogopite is more common if we have dolomitic limestone or dolomite or dolostone. Then phlogopite is common. And phlogopite is a species of biotite. A true biotite example is actually in Tasmania, Mount Lindsay. There's over there, there's a black, brown kind of biotite. It's really biotite. And over there, there's early silicic garnet, and then after that, there's a amphibole. This hessensite. Then after hessensite is biotite replacing the hessensite. And are also veins of biotite, fluorite, and cassiterite and quartz. So that's a fairly late stage, some stage. So biotite in skarns can be fairly late. Watch out for that.
Zhaoshan, just a quick question. You know, a lot of times, if you're in a porphyry system, a normal porphyry system, your early high temperature alteration is biotite K feldspar. However, in a porphyry skarn environment where you've got lots of calcium in the wall rocks, is it typical that you just have more of the calcitic alteration at high temperature as opposed to the potassic alteration at high temperature?
The albite alteration is, it depends. Some of the albite alteration in skarns at high temperature, equivalent of potassium alteration. And some of them actually could be lower temperature. Even in porphyry deposits, it's probably more related to the protoliths. If the protolith is direct, first direct kind of combination, there's more sodium, and there's probably more sodic alteration. Far southeast in the Philippines, that's a typical porphyry deposit. And there's the early stage is crisp alteration, secondary biotite, and the second stage is chloride, white mica, chloride, and albite alteration. And the third stage is aphilic. So sometimes in North America, in Yarrington district, it was proposed to be fairly deep, because over there it's deep. But far southeast is only about 1.5 kilometers, very shallow. So the depth probably may not be a control. It's the protolith might be a major control in terms of sodic alteration in even porphyry, and both in porphyry and skarns. And there's
go ahead.
Es un punto importante que puede tener alteración de órbita o cuestión sólica en sistemas en porphyry. Este control es más por el protolito. Por ejemplo, un gabro, una diorita, que normalmente son más ricos en sodio, en el centro de un sistema porfírico puede tener no tanto feldspar potásico, pero albita, ¿ya? El control del protolito, de sodio en el protolito. In skarns, there's a type of skarn is iron skarn. So the iron skarn typically is related to more mafic intrusions, diorite, monodiorite, sometimes even gabbro. And in iron skarns, very common to have albite alteration of the unit. Probably again because the intrusion is more mafic, there's more sodium in the blood. También en scans de fierro, operación albítica es muy riesgo. Obviamente por el composición mágico del porphyrico. Okay. So next one, prehnite, and this one may be reflecting under microscope give a cloudy appearance. This prehnite. We also have chloride alteration. Chloride is again iron and magnesium solid solution here. So if it is magnesium rich, it's lighter color. If it is iron rich, it will be darker color. And this one, the iron rich one, can all the way go to black color. So in addition to dark green, it actually can be black. So if it is very iron rich. So how do we distinguish chloride and epidote on the hand specimens? Color, yeah, that's color. The hardness is an important one. So chloride, if it is greenish color, and if it's light green color, yellowish green and hard, then we're still needle
that epilogue. And it will get softer than your steel copper needle. That's correct. And it can also be easily confused with parchment if you have parchment inoscar. So it's all inside the intrusive rock, all green color. And so how do we know whether it's parchment inoscar or it's a chloride in polyolithic ology? And again, the criteria, as Karen mentioned, is always pour out your hardness, check the hardness.
We have difficulty here identifying or separating chloride from finelite when it's fine. Yeah, in the alteration and the intrusion, like replacing the matrix, the intrusions, it's just very hard to separate.
Yeah. Well, it's quite to use the hardness, yes. I think is there a difference in the flow? The trick is sometimes chloride replaces parxin or amphibole. They keep the original shape. They pseudomorph the shape. And some in King Island in Tasmania, the tungsten star, the amphibole or the parxin is this big. And you clearly see the prismatic shape and radioaggregates. The only thing is you stretch it, it's very far. So it's chloride pseudomorphing the amphibole or parxin. And this copper needle, this is actually easy to get. And you have the copper wire, some of the thick copper wire, you buy the wire and you just cut it and take out the plastic cover to get this copper needle. And it'll be very useful because that's one of the hardness. Tell many part. The mind can easily organize and buy some copper wire, cut them up, and just make a curve and tunnel it here. So,
¿Cuántas personas tienen ¿cuántas personas tienen cobre para rayar los minutos? No hay. No tienen que get them.
Then you polish it and make it look good. Okay.
It's important to consider that it's very common with the heart. So there is some special studies on the
Yeah. We're talking about biotite again. So biotite actually, biotite in porphyry deposits can be your primary biotite, secondary biotite, sometimes in quartz veins. So quartz A veins and with biotite and magnetite and quartz and anhydrite, you can actually have 4 minerals in the A vein. That's the high temperature one. There's another one is, Alex mentioned, is in calcium hornfeld. And there one type of calcium hornfeld is actually biotite hornfeld. It's in the hornfeld that disseminated biotite and makes it look brownish color. So that's also higher temperature, even higher than the hydrothermal biotite, because they form before the biotite. So that's very high temperature, and then you get low temperature.
Is that your question, Alice?
No, estaba comentando sobre la dependencia biotita en los porphyrys que tenemos aquí.
Okay. Okay, so those are the mineralogy. Others, if you have magnesium-rich dolomitic limestone or dolostone, then you can have another site of minerals. So if there's dolostone, you actually can start to have olivine. Here, probably it doesn't get to the dolostone. It's probably dolomitic limestone. So olivine, the most common one is phosphorite, the green color. And sometimes we can also have the solid solution between phosphorite and the calcium end member. and that's become monosilite. This one in Grasberg, Earthberg, there's quite a bit of this monosilite. Other places you may be dominated by only phosphorite. And this one is green color, and you also can have phyolite. This one is iron member. Well, according to what we have talked about between magnesium and iron member, what do you expect this color to be? This one is black. Black. So some of them, like in Montana, there's this chromium nickel and PGE deposit, still water. And over there, lots of phyolite. It's actually black color.
What color is phosphorite?
Green. Yeah.
Light green or dark green?
Light green. And if there's, like in those peridotite, they are actually kind of translucent kind of green. The only thing about this one is olivine, like in olivine in ultramafic rock, they very easy to be hydrated. So in current day, you don't really see much olivine. So current day, what you will see mostly is, so this is a sequence. This is high temperature, and then this olivine changed to humite, clinohumite, and chondrite. And Pericles is typically a metamorphic. In dolomite marble, you can have disseminated Pericles. This is magnesium oxide. So not common, small amount. In sections, you may see this. More common is phlogopite. And so this one changed from here, it changed to here. And then from here, it changed to phlogopite. And phlogopite and talc, and that's typical assemblage. And phlogopite is, you can have crystals this big, smaller crystals and big crystals like this. And phlogopite is green color. So biotite is brown and black, and phlogopite is always green color. Okay, and brucite is a replacement of Pericles. So those two are connected. Then eventually, the end alteration is serpentine. You can have just a whole lot of serpentine. Serpentine can have all sorts of color. It can be black color, red color, dark red, and green, and white. And so all sorts of color serpentine. And that's where sometimes if a whole bunch of rock is serpentine and igneous pathologists go over there, they say, oh, this is ultramafic rock, peridotite, because ultramafic rock typically also get hydrated to serpentine. Watch out for that. If the wall rock, if that kind of serpentine, the surrounding rocks are dolomite, and think about that actually being a skarn, magnesium skarn, has been hydrated eventually to serpentine. In China, there's a lot of the iron. In northeast China, there's iron and boron deposits, and those are mostly serpentine. And then it was, I can't remember, it was a French or Germany pathologist over there. They said, oh, this is peridotite. And then everybody follows, say, oh, this is peridotite. Watch out. Again, one of the example you can actually, one of the things you can use to tell them apart is really getting into the argument is look at the magnetite. Magnetite, look at the vanadium and titanium content. So if there's igneous magnetite, you have vanadium and titanium weak percent, more than 1%. If there's hydrothermal skarn, the vanadium titanium will be low, less than 1%. So the easy thing to tell them apart. So again, watch out for that kind of situation. Some people misidentify. magnesium skarn because it goes to mostly to serpentine.
So talc only forms from alteration of olivine. Is that right? Or can it form in other ways?
I don't know exactly. So it has to be magnesium rich.
Yeah.
Another possibility is dioxide. Whether
So alteration of dioxide maybe ultimately form talc. Yeah.
possibility.
And then talc will be altered to serpentine.
They can be coexisting with serpentine.
Okay.
And it's also an end member. End product.
It's important because talc is important for the
fission. Yeah.
flotation. Is it's hydrophobic or hydrophobic? So it interferes with it. So it's good to get that understanding of how talc forms.
And talc and also is slippery. It can cause landslide and heating. Yeah. Mount Light actually has Mount Light is mostly related to prophyllite actually. That's related to prophyllite. It's underground cleaning a lot of that. The talc and also trips because it's slippery.
But so is that.
Our geotechnical areas, do we have to go into those magnesium rich limestone?
Some of them are the saline limestone, they're magnesium rich, but that's probably more related to the actual.
Yeah, and serpentine identification is you go to the drill core, you put your needle, use a copper needle with a little bit of low angle, and try to track it. You feel whether it's slippery. If it's green color or it can be other colors, just if you feel it's slippery and it's softer than your copper needle, it's a high possibility to be serpentine. That's one of the ways to identify crystal.
Yeah. Another question: would you expect talc in a proximal scan or more of a distal from the inclusion? Not quite distal scan, but at the scan more proximal or distal.
We don't have many magnesium scars, so we don't have much knowledge of that. The only thing I did my bachelor's degree on the iron scar, which is a magnesium scar. So it's typically the serpentine is more away from the intrusion. Closer to the intrusion, the dioxide, they don't change very much. The olivine gets hydrated much more, and the dioxide doesn't get hydrated. And so the intrusion is here, and there's lots of current day, there's lots of dioxide around here, then it's all part. That's a lot of serpentine. Yeah, I imagine the talc will probably similar to the present position of the serpentine. Yeah. Okay. So that's another side of mineral. Okay. The next topic is the classification of skarn. And so there are many ways of classifying skarn. One of them is look at the mineralogy and think about the composition. So if we have a whole lot of garnet, earthium, malachite, graphite, calcium-rich platinum, etc., they're rich in calcium. The protolysis is likely limestone. So this one is for calcic skarn. And another side of mineral, you see lots of serpentine. You see lots of serpentine and phlogopite, and that's the typical mineral. Talc, actually not very common in magnesium. And you see a lot of this actually because they can turn lots of magnesium, and so their protolysis is dolomitic. So that's they will be for magnesium. And subtype of the caustic skarn is if you have a whole lot of mineral like the hansenite and spacetine is garnet and rhodonite and samanite or bostonite, a whole lot of brown to pink mineral. This one, some people call it manganese. This one is actually the ore contain calcium, so it's a subset of caustic skarn. But they have specific meanings. So they typically form a relatively lower temperature. They are relatively distal, and they typically related to zinc, lead, silver, and even manganese mineralization. That manganese is not manganese in those silicates, but manganese in sulfide, which is alabandite. Alabandite, Ushitagwa, you guys know, that's a typical example of there. And alabandite, identify that it's a prismatic kind of stubby mineral. The feature is you put your acid on that mineral, it gives out a very, very stinky smell. It's a very stinky smell. It's an alabandite. So,
in cases of copper skarns, where you've got gold-emitted host rocks, are the magnesium skarns on? Is that a...
Yes, yeah. So it can be magnesium skarn producing copper. Yeah, it can be all sorts of metals, just like the caustic skarn. Yeah. The alteration is one aspect, the mineralization is another aspect. Sure. Okay. Another way of classification is based on economic metals. And so simple things. If it is dominated by iron, you can call it iron skarn or copper skarn or nickel skarn. And so very simple. But a little bit of complication is what called for magnetite. So magnetite can be abundant in many types of skarn. In copper skarns, many of the copper skarns actually have, in terms of volume of magnetite, the volume of magnetite may be more than the volume of sulfide. And I haven't seen Chalcobamba, but you mentioned a massive magnetite in Tia over there. There are also some places just massive magnetite. So the magnetite can be abundant in copper skarn, in gold skarn. In China, there's gold skarn called Beiya, that's about 10 million ounces of gold. And the discovery actually is because of the magnetite. And it's in Yunnan province, there's lots of weathering. So the farmer complain because when they plow their farmland, their plow gets damaged very quickly. Because in the soil, they're just bean size magnetite. And so some of them bigger like this, some of them smaller, it's just like bean size. So a lot of magnetite in the soil. And then they eventually find a place, then dig up, and actually there's cyanide. Cyanide porphyry, inside cyanide porphyry, there is veins of magnetite inside the cyanide porphyry. And then at that time, people call it, oh, this is exploration stage, this is porphyry step. But actually later on, you go to the site of the contact margin of the cyanide porphyry, massive magnetite. So magnetite and iron. Lots of gold, small amount of copper. So that's magnetite together with gold. And even you can have magnetite together with tin. This is reduced intrusion, but you still have magnetite. Mount Lindsay in Tasmania has lots of magnetite. Pinnacles in Queensland, there's regolite, there are also lots of magnetite. So magnetite can be related to many types of
aren't some gold skarns associated with purite?
It's very common, more common for gold only skarns related to purite. Yeah. Gold skarn is a bit complicated. Gold skarn can be related to oxide magma, can be related to reduced magma. the one related to oxide magma typically together with copper. The one related to reduced magma, they typically have lots of, because it reduces lots of pyrrhotite, arsenopyrite, even lollingite. That's good. This was a simple concept. The only thing is because iron doesn't make money, so they don't get mentioned. But in reality, if you see lots of skarn, you will notice it probably. And in recent years, it got complicated because the concept of wish deposit, IOCG. So there are many of the geologists, there are not too many, and there's little copper or maybe gold, maybe no copper, no gold. It's again, our industry sometimes have strange practices.
And can you have an IOCG deposit that has skarn alteration in it?
If you look at the definition where the IOCG comes from, Olympic Dam, and that's the most, that's type of locality, and you go to Ernest Henry in Glencoe district in Queensland, there's no skarns. And that texture is typically, you have fragments, either granite fragments that's in Olympic Dam, and in Ernest Henry, there are fragments of andesite porphyry. So those ones has potassic alteration. And then those breccia is the main texture of those IOCG deposits. You have the breccia, and the cement is magnetite or hematite, and then with biotite, with calcite and chalcopyrite and gold. So over there, all the magnetite and copper and gold, they're in the cement of the breccia. So that's the classic IOCG deposit. And then people start to take it by the meaning and say, oh, IOCG, if I have iron oxide and copper and gold, for IOCG. That's where it starts to get chaotic. So I went to do field work in Mongolia, went to Hamargatai, middle of nowhere, and there's a geologist, Canadian consultant who was logging Freeport, and I looked at all skarn, parachute, adidot, magnetite, copper. They said, oh, last year I wrote a report that this is a skarn deposit. But now I'm changing my idea. He said, I was thinking about it. So watch out. Yeah, so if you have skarn deposit, you have this assemblage, it is a skarn deposit. Good. Okay, and also many of the skarns are polymetallic. And we will talk about the metal zonation a little later on about metal zonation, and we will see the polymetallic nature of the skarns. So actually, if you don't have a polymetallic skarn, okay, looking, you may have other metals in the poly.
Si no tienes zinc, plomo y plata en tu scan, sigue buscando. And puede ser yeah, if you are looking, you look at copper moly, then you may have zinc, lead, and go over. And another common association is tungsten and moly. So when the magma gets more fractionated, granitic magma rather than dactylic or acidic, then you turn to have moly and tungsten together. Porphyry moly deposits, you probably hear about Henderson and Climax. They say it's porphyry moly deposit. But if you go there, actually there's also wolframite tungsten. In China, many of those among the top 10 tungsten skarns, 4 of them actually is byproduct from moly. So they just occur together.
Another type of classification is endoskarn versus exoskarn. And so exoskarn is replacing the wall rocks and typically carbonates. So because it's replacing the carbonates and the water out of the magma is slightly acidic, so you will dissolve the carbonate. And the end product is that because original bedding has been dissolved, you just end up with massive. So that's the typical texture for. And in the skarn, typically, it replaces igneous rocks. And typically, they may occur as veins. So here is a granite porphyry. See the big phenocryst of Cape feldspar, and that's porous phenocryst here. So this is garnet vein, and another example, garnet vein with a halo of green paraffin. So these are all endoskarn veins. And this is from America. This is from Morelos in Mexico. Again, garnet vein with green paraffin halo. So that's endoskarn versus exoskarn. Typically, yeah.
How do you identify an endoskarn that's 100% replaced?
Yeah. It's 90%, 80% of chance you will have a little bit of residual part of the igneous rock. So typically, if here is 60 centimeter is the interval. If I see in two trays, so 1.2 meters, if I see a little bit of igneous, I call it endoskarn. Then it comes to the question James asked, when the veins eventually coalesce together and they become massive. That's the case at Antamina. There's just no residual igneous rock at all. So at that time, we can't use texture anymore. We have to go into whole rock analysis. And for that whole rock analysis, remember your center acid, aqua is not enough. You have to go to 4-acid to get the trace elements. And that trace elements, you have to use those high field strength elements. So high field strength elements, HFSE. So that'll be titanium, yttrium, zirconium, aluminum, that kind of elements. It turns out in Yanacocha, it's the titanium yttrium plot. It's one of the best plots you can separate endoskarn versus exoskarn. On the other hand, you have to watch out, because if they're pure limestone, they don't have anything. But if it is dirty limestone together with the clay, there are actually also some of those elements, especially aluminum. So having high titanium doesn't automatically mean it's endoskarn. Because the dirty limestone, when those ones are changed to skarns, you can also have high titanium and those ones also. So the one we at Yanacocha is titanium and yttrium, and then the igneous cluster around here, and the exoskarn cluster around here. This is pure limestone. They don't have anything here, and when you have more clay, you will also have more titanium and yttrium. The only thing is the igneous rock is here, and they are different from the wall rocks. So then it comes to the question, can we use the same plot everywhere to tell them apart? Fate is shaking his hand. I totally agree with your Fate, and because if you have over there is a quartz monazite porphyry, your accommodation happen to be here, and your clay accommodation happen to be here. And if you go to a different area, your igneous rock may be different, and they may be here, or they may be here, or they may be here. And your wall rock clay combination depends on the province where the clay, your combination may also change to here or change to here. So the first thing is to try those elements to first see whether they can separate the igneous rock and the wall rock. And if you have that parameter can separate those two, then on top of that, then you plot out the skarn and see whether you form passes. So it's a case-by-case application should be applied this way. Okay, yeah. Well, next, sometimes the veins are very common, but you may also have disseminated. So this is Yanacocha, and so these are disseminated patches of garnet. So they are not veins, and you can have different styles of indoskarn. And typically at the contact, the indoskarn get so extensive they can become almost massive. And no matter you start with disseminated patches or start with vein, you get to the contact, they become more.
So is that relic porphyry texture down there on the left, on the bottom?
So this is still igneous rocks.
Yeah.
Yeah. And they still have this here. Okay, watch out for texture. At Antamina, at the beginning, people say if the skarn is replacing the igneous rocks, they should have this mottled texture, so patches. So even this massive skarn, you see their patch more lighter color, a patch more darker color, that kind of patches. And they say, oh, could this be the texture we can use to identify massive indoskarn? Well, based on the geochemical analysis, after we do the geochemical, then we go back to the photos of the indoskarn and exoskarn. Actually, it turns out this one is not reliable. Can't do this. The reason we thought about that is probably because if you have dirty limestone and the clay in the limestone is in clusters, you can also end up with a mottled texture. So the word mottled texture. So, not a reliable texture to tell in the term. Okay, so that's indoskarn versus exoskarn. Okay, okay, so that's from the compass. So sometimes you see in igneous texture, you see this is red garnet as vein. Okay? So there are veins of red garnet, and actually outside the garnet, as in other examples we have shown, you may have disseminated person. Again, how do we know whether it's all green color? How do we know it's person or chloride? You don't know just by looking at it. You have to scratch it and to test whether it's person or chloride. Okay, this one also have moly disseminated there. And that's another example. This is much more person, but you still see a little bit of garnet as roughly as a vein. And here happens to be this vein of garnet is overprinted by another vein with moly. Okay, with moly, and see here around the halo of this moly vein, in this darker green color, you scratch it. This is really soft. This is real chloride. So you have to take out your scrapper. Okay, so we have lots of indoskarn in Bangladesh. Okay, so those are the most of the basics. Any other questions? Okay, let's move on to, we want to take, well, let's finish. There are 2 slides, 3 slides. Then we'll finish, then we'll take a break. Okay, so this is, I'm going to talk about the forming processes. Very simple, no phase diagrams. Okay, so this one is a photo showing white and north of the North Island in New Zealand. So New Zealand is several islands, and this is the small island. You see the plume come out of the degassing at the crater. It turns out this plume, within 10,000 years, you can discharge about 300 tons of gold, about 10 billion ounces of gold, and 1 billion tons of copper will be discharged together with the white plume. Yeah, so this is, and if you go to measure the temperature here, it goes to 850 degrees Celsius or higher. Well, you think about that in nature, what kind of environment will give you 850 degrees Celsius? Has to be magma. Okay? So even metamorphic processes, you go to the highest rate, you may get to 550 degrees Celsius and so this one has to come out of magma. And so the magma typically contains the metals and also the volatiles. And the plume is mostly H2O, so that's water, and it has HCl. Well, we don't call it hydrochloric acid yet because this is a gas. If they don't condense into water, then they don't dissociate and it's not acid yet. Okay, and you see the sulfur here is oxide magma, so the sulfur is oxide species. So this one sulfur 4+, so SO2. Then we may have CO2 especially if the magma is more mafic or more alkalic, they can contain more CO2. And they may have a little bit of HF and boron. Volatile. So magma itself can give us all the ingredients, well, the other half of the ingredients to make skarns, and the metals. Okay, and that's where we take the measurement here, and it can be higher than 850. And so that's some of the fluid inclusions. It's showing this one in the quartz phenocryst, and this one happened to be, this one is formatine granite. So even it's a granite, and you see this is the fluid inclusion. So this is a little cavity inside the mineral, maybe 20 micron, maybe 50 micron, and this one is bigger. This one is almost 200 micron. So they make good photos. So this cavity actually captures the water from where the mineral forms. And so because this is quartz phenocryst, this one, the water is very early in the evolution processing. And if we look at the combination of the fluid, that will be your original magmatic hydrothermal fluid that later on form all sorts of mineralization, whether it's porphyry style or Grayson style or skarn or high sulfidation epithermal. This is the source fluid. When you look at the fluid combination, this one is a crystal of halite, so sodium chloride. So it's high salinity in this fluid. And you also have those crystals, it contains iron and potassium and chloride. So this magmatic hydrothermal fluid is rich in iron. Another example, this is where I did my PhD, and you can open the rock and then just go look for those cavities. The water has been leached out, has been lost, and the crystals are preserved. So there's potassium chloride and there's iron chloride inside the cavities. So that's all the evidence showing the magmatic water has lots of iron. And later on, the technology developed and use laser ablation HPMS to measure the accommodation of those single fluid inclusions. It turns out the iron can be up to 22% iron. So people in porphyry community, they always care about copper and gold. This one has high copper. It has 8,000 ppm copper. Wow. Look at the iron. It's 22%. Right? So way, way higher than the copper. So you think about that. We have skarns. We start with the limestone, which is only have calcite, no iron, no metals. And you form a garnet skarn dominated by andradite. The andradite has more than 20%. Where does the iron come? It turns out the magmatic water can give you enough iron. So when we talk about the formation of the skarn, it's two end member. One is your local rock, is your limestone, maybe your pure limestone, or dirty limestone, or dirty limestone with chert, or local limestone. The other end is your magmatic water. And so the water carries something and come here, then react and form. So when you think about the accommodations, you need to think about what's locally providing and what has been brought to the site by the hydrothermal fluid. So this is the hydrothermal fluid end. It contains lots of iron. So we talk about the magmatic fluid will give you a lot of iron. The magnetic fluid will give you a lot of iron. And also, because this is hydrothermal, your magnetic igneous rock, you have quartz phenocryst, and that means it's silica saturated. And the water was in equilibrium with that quartz, so your water also have lots of silica. So just by the magnetic water, it provides the silicon, it provides the iron, then you locally have calcium. That's enough to make your garnet and everything in a bit. Okay. And aluminum, as Tim mentioned before, aluminum typically has very low solubility. Remember, this is one of the high field strength elements, so they always have low solubility. So that means aluminum from the igneous rock, the transportation will be very short distance. If a longer distance, you run out of aluminum from the magmatic fluid. So you will run out of the supply of aluminum from the fluid. Whether you have local supply of aluminum, that's another question. Okay, typically it has low solubility except when acidity is very high. If you have pH less than 2, then you can dissolve the aluminum. But it's very rare in the carbonate environment because we have lots of carbonates. The carbonates will buffer the acidity. Or if your fluorine content is high, fluorine and aluminum has a very strong bond. So they can be supported. Okay, so watch out for this. Okay, and that's the magmatic side. So remember, we have something come from magma, we have local rock. So what does the local rock contribute? Then again, you look at the rock type and you think about elements. If you have limestone, it's pure, then you only have calcium. Some of the limestone may have chert, some of them chert has nodules, and some of the Proterozoic rock actually has bands. And so either nodules or bands, and then you start to have silica supply from the chert. If it is dirty limestone may have quartz and feldspar and clay. So the quartz and the feldspar give you the silica and aluminum. And the clay actually give you much more aluminum, but a little bit of iron and magnesium. So clay have those. Phingite, if it is elite, then phingitic elite have those iron magnesium, then you have selenite, magnesium rich, etc. So clay have those supplies. You may have calcareous shale. Well, in calcareous shale, your calcium is less. So you may have only 5% calcite, 10% calcite. So you mostly have your silicon and aluminum and a little bit of calcium and a small amount of iron magnesium. If it is dolomitic limestone and dolostone, so on top of the calcium, you also have supply of magnesium. So you think about the supply of elements and what minerals and they can make. And then we have the chemicals from the igneous, from the magma, then we have chemicals locally available. And then another condition you have to consider is the temperature. If the temperature is high, well, then your silica and your calcite, they will have to react. If they are next to each other, they will react. And they will form simple reacquisition, you will form wollastonite. If you also have iron brought up to the system, then you can form a anodite, or depends on the redox state. If it is oxide, you form anodite. If it is reduced, then you form anomagite. So garnet and hurt. However, those ones need higher temperature. If your temperature is low, then the quartz and the calcite, they just sit next to each other and nothing, no reaction. It will be the assemblage of quartz and carbonate sulfide. That's salt. Okay, so also think about this temperature. Okay, I think that's all my slides for the forming processing. Simple. Okay, let's take a break. I'm back.
We have coffee and biscuits arriving in 20 minutes.
Oh, and then
Yeah, cafe.
we continue.
Well, la pregunta es, ¿podemos continuar por 15 minutos? Yeah. Yeah, and I'm ready for you.
We will continue.
Cafe. Okay.
Nothing to bring you. We tell you.
Snacks are on the way from a temple to a lunch, and then it was blind. So the snacks have watched for a while.
Yes. Let's continue. So okay, okay, let's look at the next step of so the next topic we'll look at the paragenesis. The current from high temperature to low temperature, so we have a paragenesis, and it's not directly related to zoning, but it's a fundamental part of the zoning. You have to know this before we talk about the zoning. Okay, so the paragenesis stage we can have typically after the summary of many skarns, we can summarize that into 5 stages. Okay. Stage 1 is when your magma comes up and the water hasn't come out of the magma chamber yet. So the only thing you have is the heat from the magma. And the only thing happens with that heat is contact metamorphism. Okay. So sometimes we say contact metamorphism, but it can be a little bit more broad because the effect, the driving force for what happens here is heat. So this one actually, if you have regional metamorphism, you can produce the same thing. Because regional metamorphism, you also have the heat. Okay, so that's metamorphism. So during that stage one, we can generate marble. That's very easy. Everybody knows they will generate marble. And depending on your process, you may also have reaction scars, or you can have calculated form files. So they form in the stage one during the metamorphosis.
So if there's no fluids or no contribution by the magma, what reaction skarns can you form?
We'll look at the examples a little later. Yeah. Okay. So this is we'll go give you a overall picture first, then we'll look at the photos. And so after that, the water starts to come out of the magma and the high temperature, and so they can be 600 degrees Celsius, 700 degrees Celsius. So those are high temperature, and you form garnet, pyroxene, wollastonite. If it is more distal, the temperature is lower, then we have rhodonite. And we can have calcium plagioclase and can have scarpite, minor amount of scarpite. So that's the typical alteration assemblage. And you may not have everything, but you may have 2 or 3 out of this. The typical feature of that is the minerals may be rich in iron. Garnet may be rich in iron if it is oxidized. Pyroxene will be rich in iron if it is reduced. And also this will be typically zoned. When we talk about zoning pattern, when we talk about the alteration zoning pattern, we're actually only talking about the progress stage. Okay. Okay. And then intrusion may have sodic alteration or potassic alteration. It depends on the composition of the intrusion. If it is more felsic, you may have more potassic alteration. If it is more mafic, you may have more sodic alteration. Okay, the intrusion have that alteration and or Skarns, and that's important. So we may have. So after that, the temperature decreases, and then we start to have retrograde. And the retrograde, we can have retrograde A and B and C. So the temperature is continued to drop. So retrograde A, the typical minerals are epidote and actinolite. And we also have bazilbanite and scarpite. Is not very common, but some of the deposits, one of them in Montana, and lots of scarpite. And uvite, uvite is that black mineral in zinc-lead skarns. It's more common to use uvite at this stage. And we also have quartz. This is at this stage. And so at this stage, in the stage 2, the temperature is so high and the metals are dissolved in the fluid and they don't come out. And when you come to retrograde A, the temperature is lower, and then you start to have those high temperature metals come out. And that's typically iron. And so hematite is this stage and magnetite is this stage. And you may also have slightly earlier hematite, slightly hematite, filled more by magnetite. You have name murcatavite. Again, murcatavite has been known in science for a long time. And then the LTG guys come in, some of the LTG guys, they probably have murcatavite. Murcatavite is a diagnostic feature of LCD. No. If you do your homework, you know, people know about murcatavite for a long time. IOCG, the first time the term came up was, I think it's 1981. Isn't it? Okay, and also that's iron, and if you have tungsten mineralization, K-dite and wolframite come out this. Then the temperature is lower, and then even those minerals are no longer stable because the temperature is too low, then many of them change to chloride and quartz and carbonate, and that's the typical cyanide. Quartz, carbonate, and chloride. Then occasionally you may have biotite, and you may have K-phosphor, and if there's felsic magma, you start to also have fluoride. And so that's alteration. The minerals together with metals together with it is sulfides, sulfur salt, like phenolite hydroxide with a sulfur salt, electron. Watch out, we have gold, but the gold is almost never a native gold. It's typically electron. It has up to 40% silver together with the only time you have native gold is what type of deposits do you think? Only organic gold deposit have is when you have more than 90% gold, and that's native gold. Otherwise, it's just electron. Porphyry deposit, a few porphyry deposit has native gold, but still all the hydrothermal deposits, porphyry, skarn, epithermal deposits, they are all electrons. You know why this reason? Because silver is transported by chlorine, and we have those high chlorine in the magmatic hydrothermal fluid, so the silver is transported, and then deposited together. So very, very well, we haven't seen any gold in Skarn deposits as native gold, always electron. Another one is if we have tin, cassiterite typically comes out at this stage. It's later than tungsten. Okay. Then we always have the latest stage is a barren calcite vein. So they may be depends. Sometimes it's very rare, sometimes it's abundant. They're just calcite vein cutting across everything. May or may not have little pyrite, and that's about it. No other. So that's the latest one, very low temperature. Okay, so that's the 5 stages. And stage 1, metamorphic, and then 2, 3, 4, 5 is hydrothermal. The temperature continuously drops. And watch out, this table doesn't cover the scars caused by metamorphic. Good. We do have that kind of deposits like watershed tungsten scar in Queensland. Some of the gold scars has been in debate. It could be caused by metamorphic hydrothermal plate. And scars replacing by igneous rock is not covered here either. So there will be slight difference. But so far, we're looking at mostly hydrothermal scar. Okay, now let's look at more details. So garnet pyroxene, you guys are very familiar. And maybe those calculated form files or reaction scars may not be that common, so we'll spend more time there. So during this, you see, during this contact metamorphism, that means you have a magma coming up, and there's no water released yet. So the only thing happens is contact metamorphism due to the heat. And then some of the reactions are very simple. If you have a sandstone, you end up with quartzite. Have a shale, you become a hornfels. A limestone, you get a marble. That's the other one. Once simple. The only thing it becomes complicated if you have a special kind of wall rock. This one is calcareous shale. Calcareous shale is on top of, in addition to those clay minerals, you may have 5% or 10% calcite. You can't have too much calcite. If there's too much calcite, it becomes mar or change to dirty limestone. The combination changes. Well, if we have this kind of combination, then we will end up with a toxic hornfels. And well, the difference between the calcium hornfels and the hornfels is the hardness and the color. So normal hornfels, it's just the shale that metamorphosed it's slightly harder than the shale, but still use your copper needle, you can still scratch it. Slightly harder, not too much. But when we have this calciform files, this one is really, and you use your steel needle, you can't scratch it. That's your calciform file. So if we look at some of the examples, and that's some of the photos, you see the original bedding is still preserved. Lamination is preserved, bedding is preserved, and it just looks like a sedimentary rock. But you scratch it with your steel needle, you can't scratch it. Perfect. And typically the green color and the white color and the slightly green color, those are typically very, very fine grained turkey. If you do the microprobe analysis, you're typically acidic kind of composition. And those ones also are very fine grained. Well, in terms of the minerals, most of the time this is Persian. But if you are typing a granite around, you have high fluorine, you actually can, this one can be amphibole. So Mount Lindsay over there is, you see fluoride over there is granite, the tin mineralization, and the one I did microprobe analysis, they are actually amphibole. Otherwise, most of the time you have this color that's Persian. And now here we come this, some of the layers like this, so lighter brown color to darker brown color. This one actually is caused by disseminated biotech inside. So this one will be biotech home. And so that's the identification of those calcium hormones. Well, what's the importance for the skarn and mineralization? And I think to look at this is, this one is very fine grain. So very fine grain, therefore, is very low permeability. So water cannot flow through it unless you have cracks. It has to be cracking and to make it possible. So this one will block fluid flow. Another way to think about that is it will block the fluid flow. On the other hand, it will be a guide for the fluid flow. So if you have a magma here, and if you don't have calcium files, the water just go up. On the other hand, if you have a calcium files layer here, well, the water cannot penetrate here. So the water has to go what? They have to flow here, then turn the direction to this direction. And above that layer, your chance of having skarn is lower because the water direction has been changed. So that's the role of those calcium files. Okay, and
Este es exactamente lo que vemos en Ferrara. Ya nos muestra en las calización, se desbloquean los fluidos y enfocar los fluidos del scan, la operación, debajo. ¿Todavía tiene este punto? ¿Producción? Es eso contacto metafísico, no involucra fluidos, es solo contacto con los componentes, desde la proteína, la de caca, y nada viene de los fluidos.
And again, so if I go to a place, the first thing I want to ask is, what's your orientation of your body? And that's because that affects where your fluid will flow. And watch out for the position. If the foreign files are some distance away, they become like this, they're impermeable. If the foreign files is right next to the intrusion, remember the water release, when the water release from the intrusion, they can be explosive. So here you can generate more cracks. So the permeability right next to the intrusion is better. And here, if it is away from the intrusion for some distance, and this one being very low permeability. And this one will have water release generated cracks, and that gives some. Okay, that's one thing. Another one is mostly this is Persian, and sometimes you also have garnet. If you have garnet, that will be rich in aluminum, not iron. Why we will have aluminum rich garnet, not iron rich garnet? And you have to think about where is your supply of your iron. Yeah, will the iron come from your local rock or from the magmatic fluid?
In this case.
Yeah, the everything have to come from the local rock, and the local rock doesn't have iron. Well, very little of it. Why? What's the major supply of iron in Skarns? From the magma. Yeah, so here the water hasn't come out of the magma yet. So there's no supply of iron, and you only have local supply of aluminum. Well, you can only form the garnet and will be at aluminum bridge. Okay. Okay, so this is calcium felt. Another situation during the metamorphic stage is at the boundary. You have a shale and you have limestone. And at the boundary, transmassive level, you don't see much. But at a very small scale, you actually do see something. Because here, no water, everything is solid state. It's the diffusion of the elements. So the marble site also calcium. Well, it will diffuse for the low calcium. And the hornbells, we have lots of silica, silicon, and aluminum, a bit of iron, magnesium, maybe a little bit of platinum, sodium. So those silicon and aluminum will diffuse for this direction. So you go from high concentration to low concentration. Well, with this exchange of elements, and you have a product here on the marble side, because you have lots of calcium, then the supply of the silicon comes from here, you form wollastonite here. And then here at the hornbell side, the clay side, because there's a little more on iron and magnesium and silicon, and then you form earth. The garnet is in the middle. So this one will be only 1 centimeter or maximum 2 centimeters, and very thin band between the marble and the hornbell. And this one is reaction. This one, the Russians gave a term for bimetallsymmetry because it's one direction, another direction, and two direction exchanging elements. At this 1 centimeter scale, you do have components in and out, so it's metallsymmetry. But if you look at the whole rock, even just transmetal level, there's nothing in and out. So even it's called bimetallsymmetry at this local scale, the whole thing is still metamorphic. So that's the confusing part. It's called bimetallsymmetry, but this is really still more. And the term for this kind of scar is called reaction scar. Okay, so that's the properties. Well, what do they look like in the field? You see, this is a piece of rock from King Island in Tasmania. The one layer of marble, then this is a bit of wollastonite, then lots of garnet, then paraffin, then garnet, then marble again, then wollastonite, then garnet, then paraffin, then. So it's rhythmic kind of occurrence. If I tell you this is a reaction scar, you think about it. What could cause these reactions? Why you get this symmetrical bands?
Little shale beds.
It's the shale bed, very thin. It's not a thick shale bed. The shale bed is very thin, only about here. So the shale part has been totally on both sides. They have the reaction. So the shale layer has been fully changed. Right? Then we have the magnetite. Then we have the rock. So one thin shale bed, another thin shale bed. And so that's why we have the repeated symmetrical rock. Okay, so this is a solid rock, and what does it look like in the field? Well, that's more. If we do field mapping, and what should we look like? So if you just walk around the ground and you happen to see there's a little ridge, little groove, little ridge, little groove, you have this up and down, and then you put acid here, the soft part, marble, bubble, liquid, the marble, and this little ridge, they may look brownish, just like clay. Yeah. And then again, you need to have your friend in, check the hardness. If it is, you can scratch it, it's still soft. But if you have this case, typically you use your steel needle, you can't scratch it, it's hard. So this actually has been converted to perfect garnet. This is your reaction scar in the field. So this is in the Philippines, and this is an example in Utah. And again, you see this little ridge, little valley, little ridge, little valley, little ridge, little valley. And see again this yellowish color, you scratch it, it's hard. This one has been changed to perfect. This same prospect, and if you look at the drill core, on this site, you see limestone shale, limestone shale, limestone shale, limestone shale. So it happened to be this type of package of sedimentary rock. Then closer to the intrusion, you see the black shale now changed to green color, green and white. The green is earthy, white is awesome. That's your reaction. Reactions. Well, you think about this. This is metamorphic stage and no fluid yet. And later on, if you have hydrothermal fluid coming in, magmatic hydrothermal fluid, and they're slightly acidic, what will happen to the marble here? So it'll dissolve. Yeah. It depends on you dissolve that and you give you a supply of calcium, then you form garnet. This is metamorphic. And then depends on your speed of dissolving and formation of scar. If you dissolve it very quickly, the scar minerals haven't formed. What will happen to that, those layers? They have to collapse because you lose the things in between. Those will be collapsing. So you form a breccia. And this one will be cemented by hydrothermal garnet comparison. So you have this metamorphic stage reaction scar garnet comparison is cemented by hydrothermal. So you can have this situation. Okay, so that's reactions. And also, if you have chert in your limestone, so chert, and the another thing about marble is I went to a prospect and I said, oh, this is bleached marble. And the judge said, what do you mean bleached marble? Isn't all the marbles bleached or white? Well, turns out there's quite a bit of marble, they are black or dark gray color. Remember, watch out for this. Because marble is a concept of recrystallization. It's a grain size concept. If the grains are bigger, then it's marble. The color is not a criteria to correspond. So normally in exploration, it's important to figure out the marble halo and how white is that marble halo, the metamorphic origin. And to do that, typically I will use my hand lens, and if I cannot see any grains there, we know it's a limestone, but I can't see any grains, and that's still a limestone. As long as I can see grain sites with hand lens, or marble, because it has been recrystallized. Okay, and then we have the dark marble, and you look at this. This part is a chert nodule, so it's hard. The hardness is pretty high, so they are resistant to weathering, so they stick out of the surface. Now, surrounding that, you see a white color, and they are relatively soft. They are actually similar level as the marble. Have an educated guess. What could be the stuff? The white stuff here. Well, last night. Yeah. So remember this equation. We have this one is chert, so it's silica, and calcite here is your calcium CO3. Well, if the temperature is high enough, this one will react and form calcium silica. Yeah, this is molasses. And molasses, the hardness is 4. So chert maybe around 7, 6. And so that's why they get eroded also similar to the level. Okay, so that's this part is also reaction. That's because the reaction between the calcite and the chert. And also watch out. This part, the wollastonite is metamorphic. We can also have hydrochromous wollastonite. So don't take it as, oh, if you see wollastonite, it has to be metamorphic. It's not necessary. You can also have hydrochromous wollastonite. And also you notice here, when you form this, you have to release CO2. Yeah, you release CO2 and you release some of the material. There's a few things we need to talk about that related to CO2. One thing is because you are releasing some of the material out of the rock, to actually generate a little bit of cavities because you lose material. And so along the boundary between the marble and the calcite and the wollastonite, and you actually have tiny secondary permeability. You generate a little bit of a cavity, so it becomes secondary permeability. So the permeability is the sedimentary process. If you have a conglomerate or sandstone, that's primary permeability in the rock. And here it's because the thermal metamorphism, you actually generated some of the secondary permeability. So this one is chert. If you have clots of clay in there, you generate, in addition to those wollastonite, actually generate a little bit of garnet particles. If you have the clay and react with the calcite, that also gives you the secondary permeability. So keep this in mind because that permeability is important for the skarn formation when the water comes. If it is pure limestone, it's actually not so good because after the recrystallization, you just get interlocking calcite grains and there's permeability is low. Okay, so this is one aspect we need to think about. Another one to think about this is the CO2 here. You have to release the CO2. If the CO2 is kept here, then this reaction has to slow down or even stop, because there's so much accumulation of CO2. So we're in a plain word and talking about that. If you are reading papers and they will call this CO2 fugativity. CO2 fugativity, just saying there's too much CO2. Well, how much CO2 there is CO2 fugativity. If you have too much CO2, then the reaction is difficult to happen. It needs higher temperature, even higher temperature than you know. And what will happen, suppose if you go to a Clantree, you go to the cretons of those big cretons, and they have high-grade metamorphism. That means they are very deep. If you have very deep condition, the rocks are ductile, you don't have brittle fractures, then the CO2 not go up. In that case, you have the carbonate, you have the clay, nothing happens. And you're supposed to have a reaction skarn between them, but nothing happens. That's because the depth is too high, the CO2 is not released. In that case, we will have that. Okay, so that's reaction skarn.
Yeah, coffee break is ready.
Okay, very good place to stop. And then we finish stage one. That's time to breathe. Thank you.
Let's hear it. Between Scott and Department, the simulated goal. So I was thinking, that I was trying to remember the and the night programs and practice, and then the Friday night is double the size of the goal. I was trying to remember that when we were talking about the transition. There's some really deep skills. One called Star. I will write report for business. Writing. It's really big. Somebody on the back. Like starting to sing this. So it's on today. Actually, start. Yes. Yep. We have a year about. We control a lot of mind doesn't equals. It's very different. It's very fair. I think for a long time. Yes, it's nothing. It didn't say something comes with it. He was as me something. Oh, so people. Yeah. Sadness about they know you're looking at it.
特别蛮多的管，就是蛮多被客人的那个他们的不哦，经验的，他这是一直好几年。有点不够的，是点这个，今天这个事儿没点事儿，这个好有点，真的，跟那个一样的，还是要是往外整变，他们那里，是我要死，对，刚开始前就是这样，因为这个时候冰的那个话，但是它是能这个已经，这并不一定，为什么不这个知道？那从这样是也但是像我没上过那儿，你离得更远，离时间越近，稍微更出来一些。但是我这样子，我们2次， Find a ring.
You need Thank you. Gracias.
Sorry, I can't pour water. And then
No worries. I don't taste this.
okay. Let's start a meeting. Involved by okay. Yeah, I have one more slide. I've muted. So if you have your third nodule, if you have your third nodule in limestone, so during the stage one contact metamorphism, this is still this change to marble, and your third nodule becomes wollastonite. And then what will happen next stage? Well, next stage is when you have the magmatic water comes out, this limestone gets changed to garnet, and your wollastonite is still there. You can't make more change to the wollastonite anymore. So you end up with a massive garnet, then you have patches of wollastonite. So that's the reason if you see this kind of texture, that's how it forms. Okay, and that's actually related to the next stage. So stage two, you see the magma has come up, and the water is released out of the magma chamber. And so remember the magma chamber, the magmatic water, it has a little bit of acid, or hydrochloric acid, etc. So they will dissolve the limestone. And you are dissolving the limestone at the same time forming skarn. So this dissolution of the limestone gives you the supply of calcium and also the open space. So this way, your garnet particles can grow into much bigger crystals. So previously, reactant skarn, especially calcium felt, they're very fine grains. And here, the grain size is much bigger. And also another thing is you have also the water release has a lot of iron and silicon, so you form garnet particles. And because the supply of iron here, your garnet particles will be more enriched in iron. You have more iron-rich garnet particles. And also, you think about it, this is typically a small porphyry. The water is released and going into all sorts of directions, and the heat is released from here, material from here. Then we will go away, the temperature is lower and lower, and also your supply of material out of the magma is less and less. Because of that, you give a good lunar pattern. And that's actually the one we use the most for exploration. And that's the reason behind the lunar pattern is that you have point source and you release the material and the heat. Okay, and also we say this is stage two, then you will see stage two skarns overprint the stage one skarns. And then we'll look at some examples. So we'll have massive garnet skarn. This is antamina. And you see you start with limestone when you dissolve the limestone and then you precipitate your garnet. Remember, when you dissolve your limestone, you release lots of CO2. You lot of material, and also the garnet has higher density than calcite. the two factors made it, the skarn will be porous. We will have lots of open space between the garnet because the two factors. One is the loss of CO2. Second is the density is higher in garnet. And this one is in Antamina. This is about probably 300, 400 meters below the previous surface. So this cavities is not by the leaching of other things. So this cavities is original. And you can see the open spaces. And this one of the things is that original pottery spading texture is no longer exists. Remember, that's because of the dissolution of the carbonate, so they lose the texture. And also because of the cavities, is very good for later alteration and mineralization. So there's a lot of open space, so high porosity, high permeability. At this stage, the temperature is just too high, so the metals don't come out. But you prepare the ground for the later mineralization with those cavities. And so that's also called ground preparation. So ground preparation for mineralization. So that's this stage. Mm-hmm. And typically those that sample is very rare. So I put that sample back, very a precious sample. Typically, that open space is later on being filled by later minerals. This one is mineralization, so you see the euhedral garnet, and when the garnet is close to the open space, you grow into a euhedral shape, and the grain size is also bigger. And then the open space between the garnet is filled here by quartz and calcite, and a little bit of chloride here, then sulfides. So that's the typical assemblage, and that'll be even later. And quartz carbonate sulfides, and that's filling the indices. So that gave you the space for me. Okay. And so that example is big crystals of garnet. We can have also big crystals of persian that also give you the open space. This one is from Clancree and big crystals of blocky amphibole, and the open space later on filled by and Pacoperia. This one, another example, is big plates of the persian, again later on being filled by sulfide. So this is a good rock for fluid flow. And sometimes if you have this one again, is King Island. Remember, we showed that the thin layer being changed to perchlorate. And if you have the limestone layer or the marble layer, if you dissolve them at the same time you precipitate, if the speed is similar, then they don't clash and they will just form garnet. So that becomes a banded skarn. So one band of garnet, one band of perchlorate, one band of garnet, one band of perchlorate. That's banded. Sometimes both of the garnet and perchlorate, they are hydrothermal. In that case, the bending is not so clear. It's a rough bending. It may be a bend like this, and then this one has a bit here, and then or partly here at the time, roughly bending. It won't be like this regular. Okay, so that's another type of skarn, banded skarn. And we mentioned that we have stage one are those carboxylic cells. And once you form the carboxylic cells, can we still form garnet over on top of that carboxylic cell? We can't, because the calcium has already been changed to locked into pyroxene, so there's no calcium around available. So the carboxylic cells in later stage, nothing will happen by itself. The only thing can happen is you have fractures, and that carboxylic cell is broken up And then in the fracture, you have garnet. So this will be stage 2 garnet cut across stage 1 oxidation. Another example, this is from Mary Kathleen. This is a uranium scar in Queensland. And again, you see early stage. This is the coccygeal hormone stage parasite. Then it was cut by those stockworks of red garnet. So that's they are organic parasites, but it didn't form at the same stage. Watch out for that. Another one, this is from Marinas El Limon in Mexico. You see, this is hydrothermal garnet, and then you see the edge around here, roughly. You have a piece of coccygeal bone. So that's where this is broken up and then get cut into this hydrothermal stuff. Oh. And stage 2 will also have needle-scarred. Okay? So we have exoscarred at that, and we will have needle-scarred. As we mentioned, you can have packets and garnet, and then we have residual in as well. Another example shown before starting thing. Okay, that's stage 2. Well, stage 2, remember, we haven't seen any metals, and because stage 2, we don't have any metals. The temperature is too high. And then when the temperature is lower, then we start to have other mineral altering the early stage 2 mineral. Typically, as we mentioned, we may have abiol, xanthophyll, rejuvenite, strap-like, UVA, and quartz. Well, at this stage, the temperature is lower, maybe 450 degrees Celsius to 500 degrees Celsius to 400 degrees Celsius, and then at this temperature, the magnetite start to come out, hematite, and petabyte intense. Okay, so that's what it looks like, and well, that's the mineralogy, and we can look at also. Because this is another state, so the fluid is mostly concentrated in the exoskeleton, but there's no reason for it to be confined in there. It will flow into other directions, and it can flow into slightly more distal, and also it can also replace the igneous rock. That's where you have lots of ability. Typically, if the igneous rock only have epitode and no garnet, no parasite, I will not call it indoscar, because you can have property evaluation in porphyry deposits. You can also have lots of items. So just to avoid the confusion, if there's always some garnet, some parasite with epitode, then that will be it. Okay, and then some photos. That's epitode and the microscope. That's epitode, but this is not original shape of uveal shape of epitode. This is actually originally the shape of garnet. So this is epitode pseudomorphic garnet. So this is a definitive evidence that epitode is later than garnet. Sometimes we may have one mineral next to each other, and you say, well, I have mineral 1 here and mineral 2 here. That kind of evidence is not definitive. Okay? So, Zhaoshan may say, oh, this is stage 2, 1 is eating into 2, so must be 1 is later. Well, I'm looking at this side. Oh, this is mineral 2 is eating into mineral 1. So you just end up into an endless debate. It's not conclusive. So having this kind of factor, you can't see anything. So the definitive factor will be veins cutting across or pseudomorphic, and that will be more 100%. Okay. Okay, next one, we go to that's the example of voluminite. Voluminite is, again, regional aggregate is hard. It's typically a little bit brownish color, and it's replaced in the red garnet. And so this is from ugly. And watch out for voluminite, and voluminite has two habits. One of the crystal habits is regional aggregate. Another habit is actually granular, it's similar to garnet. So sometimes you have to go to the microanalysis to identify whether it's garnet. Okay, that's stage 3 with in stage 2. Another example, this one is this is a prismatic shape preserved, and it's kind of still green. This is under microscope. This is uveit. So this is uveit. Uveit shape is more blocky, and so this is again uveit is skeuomorphic person, and so that later on this part is separate. So that's uveit skeuomorphic evidence. And this one is showing stage 3. We also have mineralization. So magnetite is later than stage 2 prograde. And this one actually shows this is stage 2 massive garnet with a little bit of pyroxene. Then it's cut by this black vein, and then it's cut by this yellow vein. So the black part is magnetite and biotite, with also a little bit of chloride. And so that's stage 3, and then the sulfide is coming out, and that's stage 4, quartz and calcite and pyrite and chalcopyrite. So that's another example. This is indoskarn massive garnet pyroxene, and then it's cut by the magnetite vein. So that's where stage 3 cutting stage 2. Another example, this is Aranzazu in Mexico, and that's green garnet. You see the quartz and then specular hematite. It's still specular hematite, and some part is more preserved, and some other part is more altered. And this one, you still see the specular hematite shape, and you change it. It's very magnetic. And one of the things to tell, if you again have to use your pepper again. Yeah, you scratch this. If it is still red color, that's still mostly hematite. And if it becomes just still gray color, that's mostly magnetite. And the thing is, if it's partially changed, you do your magnetite change check, or it's magnetic. But to tell the proportion of that, again, you can scratch it. Well, this is fairly common in skarns. There's no wonder also in the stomachs, we also have this specular hematite and partially changed to hematite. Again, you see it filling the interstices between the garnet, and so this is the stage 3. Okay, and also we can have abidos, and also we can have amphibole. And so this one you see again, that's from Ferrobamba. In early stage, the garnet is red color. This light yellow color, light green color, this is pyroxene. And then this one is this kind of green. It's like a little bit of, it's like tree leaf in the spring only come out. It hasn't been those dark green yet. That kind of young green, and that's amphibole. So amphibole is replacing the garnet, and so that's stage 3. And then you see this one is cut. So this vein is mostly magnetite with a little bit of amphibole, and then you see this vein has cut it and displaced it. And this vein actually is the sulfide. So we have moly and chalcopyrite with quartz and calcite. And so that's actually stage 4 cutting across stage 3. That's the paragenesis. So the temperature continue to drop, and the amphibole is no longer stable, and then it changed to chloride. So chloride and carbonate. And so we mentioned carbonate, we don't say calcite. That's because you can also have other types of. So you always have calcite, but sometimes you may also have anchorite and saturite. So, and then together with quartz, and locally, if it is more caustic magma, you will also have chloride. Then occasionally you will also have iron. And also the sulfides, the metals in this state, again, will be lower temperature sulfides, and in metals, and it will be sulfides, sulfur salt, electrum. Okay, let's look at some of the photos. So we mentioned previously UV has replaced amphibole and or paraffin. This is the uveal shape of UV. You see here, coming here, that's the blocky kind of shape of UV. But now part of this is still UV. You see part of this has been altering the UV and eating the UV. And now this one is mostly siderite with the visual purpose. So this is stage 4 replacing stage 3. Another example, this one is under microscope. This is paraffin, and you see the high relief. This is paraffin, but some part of it is low relief, but it still has the cleavage of the paraffin. This one is paraffin has changed to tau. So this will be stage 4 directly replacing stage 2. Another example here is you see the garnet here, paraffin here. Then when you have a vein of quartz, calcite, sulfide vein, then you see the halo, or this halo of gray, black, gray and green color. Those are mostly chloride. You see the chloride also get into here and get into here. So that's the overprint of stage 4 directly overprint stage 2. This is a microscope in here. The garnet shape is still there, uveal shape, and with the zonation, now it has 14 chloride. So that's chloride here, and that's magnetite. So the iron in the andradite, and you may have 20. Remember, you may have more than 20% iron in andradite. We'll change the chloride. Sometimes you change it to iron-rich chloride. Then the iron is in chloride, like the black one. And then sometimes it is not black, and then some of the excessive iron will come out. Magnetite. And we mentioned where just a few more words about the magnetite. So remember, we see the garnet in calcic skarns. You have garnet and paraffin taking up a lot of the iron. If it is magnesium skarn, because you are having olivine or eventually serpentine and logophyte, you really don't have much iron in the minerals. So there's much more iron precipitate out as magnetite. So if you start with same amount of iron, then in magnesium skarn, you have much more magnetite because the iron is not consumed by the oscillation minerals. Okay, it's one comment. This is the example. You see this color is brownish when the core was recently, well, when the core just out of the ground, it's white color. And after several months or a year, it changed to brown color. What's the reason of this? Or which mineral do you think this is? Very good. It is iron. Saturate. So, but you look at the shape, they still have prismatic shape. So it's saturate, but it has prismatic shape. So why you have the prismatic shape? Pseudomorphic. Yeah. So it has pseudomorph and replace the paraffin. This one is less oxidation. This is still saturated. The black part is the solid. So the calcium and styrite replace. Another example, this is time you see those are the garnet, and every time you have sulfide, you have some quartz and carbonate and the black mineral together with it. So the black one is the black quartz. And sometimes the black quartz you see, it can actually replace certain zones of garnet. That's selective replacement. So we saw this stage 4 cut stage 3, cut stage 2. It can also actually cut stage 1. So this is example. We have the stage 1 calcium chromophores are still here. Then you have fractures, and later on we have these chloride carbonates in quartz together coming in. You see those ones are replacing. And this is the residual patch of the calcium chromophore, and that's the vein itself. Another one is biotite chromophore. So this is original biotite chromophore. Then we have a vein coming through with those chloride in that assemblage, and then you have bleaching around of the biotite. So that's again, that's stage 4. This is could be stage 1. Okay, so stage 4 cutting stage 1 of the food. Yeah, we also have the sulfide in terms of mineralization. That's parallel vein with quartz cutting across the earlier magnetite quartz. So stage 4 mineralization. This one actually is from Turkey, and this is stage 2 garnet, partially mostly garnet. And then you see those, that's a lot of epilogue. So epilogue, that's stage 3. And then the stage 3 is overprinted by the sulfides with the chloride around it. So that's stage 4. And then the whole thing cut across by this paraffin calcite vein. That's stage 5. That sample shows that the full, stage 2 to stage 5. So that's the typical paragenesis. And sometimes people may get confused. And if you see here, that's a uveal garnet, and you see the charcoal pyrite actually occur in the ring of the garnet. And people are saying, oh, look at this. Oh, this is the sulfide in the ring. It must be sulfide occur together with the garnet. Hold on a minute, and let's look at the details. And if you cut a thin section here, actually, you see this one is a progressive replacement of garnet. So this one only have the dark color, this is garnet, and the white little band, that's sulfide. And then this may be only 5% replacement. And then you go here, that's garnet, and that's the band of calcite, and that's another band of calcite, and that's another band of calcite. And actually, you see some of the calcite, eventually, they get connected with the calcite outside. So you don't see it with hand lens, but under microscope, you see better. And so, again, you have this quartz and calcite, and together exactly they replace the zones of those garnet. And by this time, you've already 60% replacement of the garnet, which is exactly this. It also has the mineralization. See, some of the mineralization is charcoal pyrite, plus fluorite, plus pyrite, and together with quartz and the calcite, they occupy some of the bands. But if you look at again, some places actually this vein is going outwards. It's not limited. Some of them are in the band, some of them are not. So with that kind of detail, again, it goes inside the garnet, that assembly is the same assembly outside. It's still replaceable. It's just the scale of the replacement is very delicate at the micron level. It's also this kind of delicate selective replacement is not only limited to garnet. And some places, the frontal high sulfur deposit, you actually see minardic replacing zones of pyrite, also at micron level. It's selective replacement. Again, if you think back again, remember when you have calcite and quartz occurring together, it has to be low temperature. If the temperature is high, they cannot stay together. They will react to form volatile. But it's still low temperature. Those ones, the sulfide is still later. Okay, nice. And when mentioned the mineralization of the later one stage, they're not limited to the prograde skarn itself. Some of them may go to beyond, they go to the calcareous frontals or marble, and if there's a vein here, they actually get mineralized into the calcareous frontal. And if you go inward, and the mineralization also cut into the intrusion, and they're calcareous vein with a halo of quartz. So, and that's typical for skarn. And this is a bit different. Even this is inside the intrusion, this is different from the porphyry veins. So remember, if you have porphyry sulfide dominant veins, it will be D veins. What's the halo of the D veins? It's typically muscovite or elan. You don't have chloride. Well, why we have chloride here? Remember that a lot of iron released out of the magnetic fluid, and then it gets replaced, and so it's still the fluid is keep having those iron, and that's ended up become a chloride around the veins. And also, typical in other environments, if the epithermal, intermediate sulfidation epithermal or low sulfidation epithermal, if you have chloride, both chloride and electrolyte, they typically, when you are getting closer to the vein, the chloride is totally replaced by the electrolyte. That's not going to. And here, you still have chloride close to the sulfur. And sometimes we have weird or fascinating skarns, and this one is regolite, as a term, regolite. And so every little black and little band, this is magnetite. Then between them, those are fluorite and quartz and cassiterite. This is from a thin skarn. So why? Another example, this is iron skarn. Locally, we just have this very regular band, and you closer this 1 centimeter, and that's the bigger bands than the previous photo, but you still see the regular band. That's magnetite, that's spermalite, magnetite, spermalite, magnetite. So that's the bands. Just be aware of this. This is. It may occur somewhere in it. Okay, so that's the paragenesis. Any questions? Well, let's move on to the thing that is more important for exploration, the building pattern. Yeah. So paragenesis is the fundamental science behind the zoning pattern. And watch out, is this zoning pattern we're going to talk about. When we talk about zoning pattern in alteration, we're only talking about alteration in stage 2. And when we talk about mineralization, we also have metal zoning patterns that will be stage 3 and 4. The magnetite is stage 3 and the sulfide is stage 4. Yeah. Okay, and with the zoning pattern, you can figure out where you are in the system. Are you in the middle part or in the distal part or close to the proximal part? Which direction you should go to find the intrusion and which direction you go if you want to find the silver mineralization, the CRD. Yeah. And also, this is a very important tool to determine the causation intrusion. And we will talk about how to identify this a little later, but this is the most important tool in the building.
Doctor, question. What is the relationship about the meteoric water during the scan solution?
Yeah. The meteoric water typically is start to be more and more important in the later stage. So stage 2 is still dominantly magmatic one. And we'll get to the amphibole epidol stage, you start to have some meteoric water. Stage 4, there will be a lot. Mixing with the groundwater actually is one of the mechanisms precipitated of the metals. Next, so this is the summary of the zoning pattern. That's this is getting a little bit complicated, and there's many things. Okay, so if we depend on the properties, we may have basalt or tertiary or fail or limestone or calcareous or siltstone, and you may have interlayered thin bed of fail and limestone, and also sandstone. So you may have all sorts of wall rock. And the first order thing is that your skarn obviously will be more common in the limestone layer, and other layers will be less. Okay, and then assuming we have the magma is oxidized and the wall rock is reduced, then we can have this pattern. So we start with the intrusion. Inside the intrusion, right at the edge, we may have massive inner skarn, and may or may not. Sometimes we don't have massive inner skarn. Then you go inside, it's just veins of inner skarn. This one typically garnet is red color. If it's green color, it's a different story. It has to be red color if there's causing intrusion. Okay, and then you can have disseminated alteration of pyroxene or wollastonite or other minerals, and sometimes even titanite disseminated in the world. So that's inner skarn. Then you go outside, we can have several parameters to show the zoning pattern. Okay? Well, let's start with the massive, the bigger picture. So we can have the massive skarn here, and then we go out, we have a bleached marble. Either CRD or bleached marble, depends on the position, geometry of the skin. And you go outside, obviously, you have a bleached marble, you have to have another gray marble, a darker green marble. So this will be darker green marble, and then you transition to the limestone. And this boundary here, that's your marble halo. How wide is your marble? And this parameter is important. We'll talk about that later. Okay, so that's the overall zoning pattern. And then this skarn, massive part of the skarn, if there's 10 meters, 20 meters, not a big deal. You will see that skarn, just walk through, it'll be fine. But sometimes this skarn may be hundreds of meters and sometimes more than 1 kilometer. And in that case, even you find the skarn, you are standing on the upper of the skarn, you can still be lost and say, oh, where is proximal location? Is that this the location or north or south or east or west? And so we need also zoning patterns inside the massive skarn. Okay. Inside the massive skarn, we can have several parameters showing the zoning pattern. The garnet color is the most reliable one. Typically, closer to the intrusion, the garnet is darker color, then you get lighter color and lighter color and even lighter color, all the way to the marble front. That's the garnet color change. Well, you say, what's the change of color? Well, this one, the good thing about garnet change is that typically they really change color, not just light green to darker green. They actually change color. Okay, this is example. This is the Mexican skarn. It's called Mexican skarn, but it's in the Philippines. So Philippines have many names, resembles North America. The mountain in the middle is called Cordilleran Mountain, but actually the is much, much smaller than the Cordilleran real America. And then there's the skarn for Mexico. And you see this is only from 38 meters to 54 meters, so only 60 meters. But you still see a good color change. This one is quartz diorite and quartz diorite porphyry, that's the collagen nutrient. You see the garnet inside this quartz diorite porphyry, that will be the inner skarn, and this one is dark red. And you go out, it becomes red-brown. And you go further out to brown color. And you go out to yellow color, yellow-green, and then you go further out, that's marrow, and already, and the most beautiful part is very light level. So that's what we mean having color change. Okay, that's there's many skarns have this pattern, and you just go away from the current color and the similarity. This is the skarn in Haribamba, and you see here that's the inner skarn, a bit of garnet, and lots of pyroxene. Then close to it, you see the garnet is dark red, and you go further out, it becomes brownish color, and then you go further out, and that's only about 8, 12, so 15 meters, and it gets to yellow-green color, green-yellow color. So that's the only pattern also happens here. Actually, this one is happened to be between two dikes, and this one showing red to brown and to yellow-green. This is darker green, but you start to see the pink garnet is getting into cutting fluid. That's even more pink, and then you become more. So you still have residual part of the green garnet there, and then you go to further out, it actually become solid red color. And then if you maybe I'm closing to a polynutrient, turns out it's a dike with skarny veins and starches. So actually it's a coalescing of two skarns together. Maybe this one is slightly earlier and got a green color garnet, and this one is slightly younger than this red garnet, pink garnet. The diesel part.
But the intrusion has no relation with the skarn. Even the intrusion is on the dike, post dike.
Well, the dike can form skarn, no problem. And this is copper mineralization, and if you go to zinc lead, it's more common also around zinc lead. The dikes are in the middle and then around further out from the dikes.
Questions? The elements which the garden has can affect the color of the garden?
That's a very good question. And we tried having to figure out why there's color change. It's just an experience. We see so many of these skarn systems at this regulation. I did some laser ablation analysis of this pattern from the Mexican, and turned out some people say it's related to iron. No, it's not related to the iron content. Some people say it's related to the titanium content. I'm related to titanium. What I found is actually related to, a little bit related to tin. The darker one has elevated tin than the yellow. That's the only thing I found.
Quite brief, and if you go forward, yeah. So the more pink garnets are very clean,
Yeah.
whereas the green garnets have inclusions of of dioxide and other minerals as well. But the color change is more related to the inclusions that's within the garnet crystals, and the more proximal garnets are more clean with no inclusion.
And that actually leads to our another parameter is garnet perfect ratio. Well, actually, the next slides are related. I will talk about that a little later. But the next slides, we're going to look at the Persian color change. The Persian color change, if it is oxidized magma, typically the Persian is closer to the intrusion. It's more diabacitic Persian, little iron, mostly magnesium. And you go out, there's more iron, and that means it becomes lighter green to darker green. And so if it is typically just the green, lighter green to darker green, this is a bit difficult to observe. So it's a bit difficult to use. But when you go even further out, especially branch skarn, fairly hundreds to kilometers away, then the Persian actually change to brown color. And that brown color Persian, eventually Persian disappears, you start to have rudiment, start to change from brown color to pink color. The pink color also changed to rudiment. And that color change actually is related to when you change from light green to darker green, this is mostly magnesium iron ratio changing. When you start to be brown, it's actually the manganese content. Well, I should say you start to have significant amount of manganese. So this one, maybe you have only small, a few less than 1% manganese or 1% or 2% in this given is green color. You still have, but when you change to brown color, that will be 8%, 9%.
Manganese from
the manganese, we believe it's still from the magma. And the thing is, the iron is deposited at a relatively higher temperature, and the manganese minerals form at relatively lower temperature. That's why they occur only at the distal part. Closer part, temperature is so high, and they only have small one. And so with this kind of situation, this is actually difficult to get the full picture of all the perfect colors. You either are in the light green color, dark green color, or many of them are in the distal part and in the brown part. Occasionally, some of the skarns actually can have a more complete color change. And let's look at some of the photos.
about the limestone. In Bambas or Mambas, at the bound formation, we have limestones. But we have a range of limestone composition in the column. So sometimes it's not necessary to all change of color. Sometimes change the vertical according to the composition of limestone.
Yeah.
We need to consider that.
Yeah, very good. We will talk about that, especially when we talk about garnet character. White limestone is more less reduced, so you will have less iron, and we will have the carbonaceous, the black one, and you will have more reduced condition. You have more reduced iron, so the color will be darker and green. And so that's why I say garnet color is the most reliable one. The Persian color, less reliable. The reliable part is only when you go to the more distal part, you change to brown color. And that's not related to the iron anymore. It's the manganese. And that will be more reliable. Okay, we'll show some photos of the Persian color. And again, watch out, I'm not showing the same deposit because it's difficult to get a full picture out of the same deposit. So this is an example of light green Persian. You see that's light green color. And this one is dark green color. So you see almost fairly dark. This is from Sepang. Yeah, this is from Laos and this is from China. a zinc gold skarn, and you see a very dark green. And then when you go further out, you start to see you still have the dark green color pyroxene, but most of them now is light brown color. That's elevated manganese. And when you really get to the very high amount of manganese, you can see that's how brown you can get. The pyroxene, and that's how brown it gets. This is the Colorado, that's Nicholas Zoom. Okay, that's the pyroxene color change. And the pyroxene color change is related to the manganese content. So here we are looking at, this is the dike. You're seeing the mineralization. This is the dike. The main intrusion is probably way here. Right? So this is the hypothesis coming off a major intrusion. And this is part is relatively more higher temperature, and that's the end of the dike. That's lower temperature. And you look at the garnet pyroxene ratio, the right one is more garnet than pyroxene, and the green is more pyroxene than garnet. And when you go further out, you run out of pyroxene and become phosphonite, rhodonite, and that's the purple. And the pyroxene content is showing here maximum Zhaoshanite. So Zhaoshanite is end member manganese. So here is less than 25%. You go here is 25 to 50%. You go to the most distal part, it's more than 50%. So that's related to the color change. How brown it is and it's related to how much manganese inside. And so sometimes if you want to really have a consistent or zoning pattern, you can do the microprobe analysis, figure out the manganese content. The light green one may be less than 1% manganese. Then you start to dark green, even if it's not brown yet, you still have a few weak percent manganese. And then you go further up. It's a good way to figure out the zoning pattern. And when you further go out, you run out of pyroxene, it become rhodonite and wollastonite. And this one, I show this photo because it's a zebra texture. It looks beautiful and can be confusing also. Because in MBT deposits, people also have lots of zebra texture. But the mineralogy is different. So here, you see all this green color, see also the prismatic radium aggregates. So those ones are rhodonite. And the one relatively more white color, those one also with handless, you can see radio aggregates and white color, that's wollastonite. So wollastonite band and rhodonite band, wollastonite, rhodonite. So this is the most distal part of this. After this, if you go further out from the rhodonite and so on, you become CRB. You run out of, the temperature is too low, you don't even form wollastonite. You just have quartz and carbonate together and with sulfides. And then you say, oh, how do I tell? People say leopard texture is MAT deposit. Why this is not MAT? And the difference is again related to temperature. The temperature actually is shown up as mineralogy. So we have, if we have here a wollastonite and rhodonite, the temperature is definitely up. And another situation, if you go further out, it becomes quartz and carbonate. And that quartz is a K. Okay? So quartz, you guys know the minimum formation temperature of quartz? Minimum 180 to 200 degrees Celsius. And if you look at the phase diagram, if you have phase diagram above this temperature, silica comes out. No matter how small the crystals are, if you see it with your hands, you see a quartz film, quartz crystal, the temperature is minimum 180. Below this temperature, the silica will precipitate out as Charleston. So, MBT deposits is very rare quartz. So their temperature formation temperature is low. So they will very rare to have quartz. If you see quartz and carbonate and sulfide together, that will be the CRD. If you don't see quartz, only another one difference with CRD with MBT is MBT, the carbonates alteration is dominate dolomite. And in CRD deposits, dolomite may occur, but very rare. And you may, mostly it's siderite, calcite, siderite, and rhodochrosite. The reason why MBT has the dolomite is because their mineralizing fluid is beaten brown. It's evaporated seawater. And seawater has lots of magnesium. So that hydrothermal fluid for MBT contains a lot of magnesium. So over there, then alteration, you generate lots of dolomite rather than iron. You don't have iron really in the MBT system. So that's the difference between MBT and CRD. One is looking at the quartz, one is looking at the carbonate mineralogy. Okay. So that's garnet paraffin. Well, that's the paraffin color. And then another one is garnet paraffin ratio. This one has to be careful because you are thinking about the same bed and this ratio will work. And if you go to different beds, there's complication. So typically in the same bed and closer to the intrusion, you have more garnet than paraffin. Here, garnet much more than paraffin here. You go here, it's garnet more than paraffin. Then here, garnet equals paraffin. You go further out, that becomes paraffin more than garnet. And then you go further out, you may have a wollastonite node here. And wollastonite dominant, and you may have disseminated garnet. With Poribamba, we have lots of wollastonite with disseminated garnet. And some of them garnet is spent. Some of them are disseminated.
If you have a very pure limestone, will you still get pyroxene?
Yeah, paraffin, because the silica comes from the magnetic hydrothermal fluid, the iron comes out of the magnet.
Yeah, but where does the magnesium come from? The fluid?
Yeah, the fluid has less. Yeah, less amounts. Still have magnetic water. So that's the garnet paraffin ratio. And same time, you also see this is Carfrock in Bingham right now. At the beginning, before they found the big porphyry, they were mining the Skarns and the CRDs and the Skarns. And now it's a big peak because of the porphyry. And that's copper and gold. And you see here, the garnet here, closer is red brown. To here is brown. Then go to brown and green here. The diesel part is yellow green. And most diesel part is green yellow. And again, this is depends on the bedding. You are in the same bedding, you can do the comparison. And in Poribamba, you have much more wollastonite. And this wollastonite here is only a thin part close to the marble hills. But if you have church in the limestone in the same bed, well, that amount of wollastonite will be much bigger. Because the properties have the right condition, have chert. And that's probably, you have a lot more chert, a lot more wollastonite going in that direction. And so the sample, some of the sample garnet is red, some of the sample garnet is brown, and some of the sample garnet is green. So if you, I would suggest you put the sample number, well, the sample location get the coordinates of the sample and put it on the map before we show a zoning pattern.
I've got a question. You've got different layers of limestone there with different distances of scar operation. What are those dark layers between?
Oh, so this one's if it is between the shale and the limestone here, this is the reaction scar and toxic chromophores. That's it. Typically on the margin between the shale and limestone, that's the reaction. Okay. And that's another example, this fortitude gold scar in Nevada. And again, you have a major intrusion, then you have this dikes coming off the majors. You see here, Garnier-Parkin ratio here is 2:1 here, 3:1 here is still more Garnier than Parkin. And then to here, it changed to 1:3. There's more Parkin than Garnier. You go further out, it's 1:5. And more distal part is 1:20. That's almost dominant by Parkin. And we mentioned the Zhaoshan component here is closer to the intrusion. It's not brown color yet. But this is just green, but you can still do microprobe and figure out the manganese content. And this one, 0 here, 0 here, 0 here, is 4 here, 6 here. So small change is subtle signature, but still show a bit of zoning pattern. To go away, you can have this Parkin accommodation showing the pattern. And I have a PhD student currently working at the Clarivata. It's one of the things he's doing is microprobe analysis of the Parkin and also of the garnet. The garnet also, remember, we can have manganese in the garnet, and it's showing a regular pattern. And trying to use that to figure out whether it's 1 center or 2 center or the 3 centers over there. Okay, that's the zoning pattern. And this one is a small sample. This is Marilla's gold scar. And just to say, this is your dark marble. And you see the crystals. Even with this, you can still see the crystals. This is marble, but the black color is there. What do you think the reason of the black color? Carbon, very good. So this is organic carbons, and so they are mostly methane. And then when you get closer, temperature is higher. They are basically burning off the carbon, and you're oxidizing and burning off the carbon. You lose the carbon, then the marble becomes white. So that's why we have bleached marble here. And this is example of massive bottom. This part. Okay. And then I need to go back to this. I should have put that in back here. Okay, so we look at the garnet color change, we look at the Parkin color change, we look at the manganese in Parkin, microprobe analysis, we look at the Garnier-Parkin ratio. And what we showed is the Garnier-Parkin ratio has got to be really careful. One of the things is the accommodation of the beds will affect your Garnier-Parkin ratio. If you have white marble or white limestone, you turn to have more garnet. And so that's on top of your hydrothermal fluid. Hydrothermal fluid is oxidized, and also your wall rock. And if your wall rock is black, carbonaceous limestone, like some of the beds here, well, even your fluid is oxidized, your wall rock is so reduced, and you can actually form lots of Parkin even at closer location. So that's one complication. Another complication, remember when we talk about those shales, if you have more shale and the shale happen to be those iron magnesium rich shale, then you can also have more Parkin than the pure limestone. So the comparison of the garnet-pyroxene ratio is need to be done in the same layer. Well, sometimes it's easy to say they're the same layer, but most of the time it's difficult to say whether we're in the same layer or not. So that's a bit of complication. Just be practically and watch out for that. Okay, so that's the major part of the skarn, and then we go out. There are also other zonings. We go out. We also have a fluid escape texture. We'll show the photos a little later. And also in terms of other lithology, here. See here, the boundary between the shale and the marble. We have this reaction scar. Okay, now reaction scar is at the same position as the marble, just because the qualities change, then you have different product. Okay, we have the reaction scar here. We also have the reaction scar here. Well, now if you change your lithology to calcareous shale or siltstone, then during the stage 1, you already form a whole bunch of calcium formula. Well, that kills the skarn. In later skarn, in second state, even the water comes out, this mostly don't change. The only thing you can change is you have those veins or fractures, and then you can have the garnet cutting into your calcium formula. We'll really come to the fluid next to the intrusion. Well, when you're really next to the intrusion, because the explosive release of the water, you get the fractures, and so you will form hydrothermal, but very narrow. And then you will see the fragments of the calcium tiles cemented by this hydrothermal. Okay, that's one type of lithology. Another type of lithology is you have interlayered thin beds of shale and limestone. So where equivalent position of the marble, you get this reaction scar. So garnet-pyroxene marble, garnet-pyroxene marble, garnet-pyroxene marble. You just get this the photo we showed with the alternating beds. When you're getting closer to the intrusion, the water comes out and the water dissolves the limestone, and the limestone part you form garnet, and the shale part is the pyroxene. And so you got this banded scar. And we'll get really close to the intrusion again when you have very high water rock ratio. The probability doesn't matter too much, and so you still end up with a massive scar. That's this type of effect. What will happen to basalt? Well, if basalt from temperature 1700 degrees Celsius, 1600 degrees Celsius, your magma, fluid magma, you may only have 800 degrees Celsius, 900 degrees Celsius. So this will do nothing to the lava or basalt lava. But watch out. Locally, sometimes right next to the intrusion, you actually can replace the basalt to form some skarns, and that's the one we mentioned, Hungan, gold, and tin, and Candelaria situation. Yeah. Okay, so that's this. And what will happen to the sandstone? Well, the sandstone will, during the first stage, you get to quartet. And then really not too much happen. But if you have a lot of fractures, you may have the fracture being filled by carmine. Depends on the supply of the calcium. If it is right next to the limestone, you may get turned. If you are away from the calcium, there's no calcium, then just have groundwater here, and then do the mineralization stage, you may get sulfides, you may get magnetite. That's in yeah. So that is okay. So that's the full picture. And that's
I have a question about talking about in the first slide. we have not too strong, but it's anomalous. In moly, the moly is well development, so very good in his or mind, the quantity. If you will relate to scan or coffee scan, also, it makes sense in your opinion about the ability of
Moly mineralization typically very closely included in Skarns. So for the possible. If you have the moly and there's groundwater and the mixing of groundwater with hot temperature water, you can cause the deposition one. Copper, zinc, lead. So, but probably not too much. Later on, we'll talk about that. And zinc lead mineralization, it actually generates acid. When you deposit zinc lead, you generate acid. If you don't have carbonate to buffer it, the reaction will stop. Will be dispersing. So the zinc lead will deposit very slowly. And that's why in porphyry deposit in volcanic rocks, very difficult to make to have a zinc lead mine. You may have disseminated or intermediate subdivision epithermal deposit. You have some sphaleracalina, but never being able to big enough to make a mine. So your intermediate subdivision mostly mined for gold and silver, not for the zinc lead. But moly is different. Moly is transported by OH. So they don't generate acid. So they don't need the buffer. It probably can deposit in those things. Yeah. For the magnetite, that's the metals only. We'll talk about that a little bit. Yeah. So magnetite will typically be closer here. Well, so then the color change. The closed magnetite will be closer, and the chalcopyrite will be lead, and then you go further out to sphaleracalina, and then you go further out to silvermine. Okay, and then we mentioned that. And for different metals, copper typically related to shadowing, and tin skarn typically related to difference, bigger batteries and difference. Zinc lead doesn't care about the size of the instrument; they just want to be away because they want to have a lower temperature. So, yeah, more peaceful.
Can you explain to me that copper and zinc? Is he zoning between copper and zinc and mean?
Yeah, and what Antamina has copper and zinc. There's zinc here, and the zinc is low grade. It's not like a zinc skarn. You get zinc plus lead 8%, 10%, 12%. Antamina is less than 1% zinc and lead. So it's too close to the ingredient. And you do, because the large volume, you have that metal, but you look at the details, they're low grade. And we mentioned, so the hydrothermal system doesn't stop at the skarn end. So the system still continues further out. That's the example. That's a big Gaussian. You see that's green pyroxene, green garnet, and then in the marble you see those halos. You see little veins. So you again scratch it. If it is hard, this actually can be green pyroxene. If it is soft, it's green coral. And so that's the system continues going on. And then you go further out. Well, some places is pyroxene, sometimes it's actually garnet and also go up into the marble. Right next to it could be little veins going into that. And some places that's Aranzazu in Mexico, see in a massive, coarse green marble. You can see the green side. And those patches, it looks dirty. It's actually green garnet. So you can have these patches of those green garnets in the marble, in the distal location. Again, this is marble, and then you have this patch of green garnet. And the Spumbus also have this situation. So white marble, then just have a patch. You see here as green garnet. And I polish this piece, and you got to use a polishing rock to get rid of the oxidation on the surface. After that, you see this is green garnet. This one didn't polish, it looks red, but that's actually just an oxide make. You can't have polishing block. And if you want to have simple things, maybe it's $2 together. Yeah, so it's just in the hardware store you buy one piece. It's called Whitestone to polish your knife in the kitchen, and you just buy this and $12 for one big piece. They cut in 6 pieces. Easy to use because it's thick. It's easy to use. Okay, so that's this part of the system. Garnet in the marble, and also the fluid escape structure will behave like this. So this is 50 to 100 meters away from the scar, and you see those relatively thicker veins. So that's nice as steel, and see this is black clay mineral and fluoride, and if it is fresh, you should have very fine grained disseminated pyrite. So that's and maybe also calcite. So when it's closer, it's wider, and when it's further out, that's 200 meters away, you see the vein gets much narrower. So they look like stellarite in limestones, like the representation, but actually it's different. It's related to mineralization. And once you see it you see it more frequently. This is Zhaoshan in China. Also see how those narrow and convoluted veins, those ones. It's black color partly because it's oxidation of manganese. So the calcite is manganese calcite in those veins. When it's oxidized, it becomes black color. And you see this one, see how convoluted it is. And that's, again, when you see that kind of feature, follow it up. This is indicative. Japan had that, and Phantom had that. Then many of the scars I went to find. You look for it, you will see it. If you don't know its importance, just go through it. You'll be done.
Does that have a geochemical picture with it?
Yeah, that's I've run a master student project, and right now I have a permanent PhD student working on those distal features. And that's an example. This is from Ushachakwa. Also, see that's the veins. And the black color is, again, because of oxidation among. And if you open up the vein, actually you see the black veins. There's black color and red color. And some of them are iron oxide, some of them is manganese oxide. And because the calcite originally is calcite vein, and if you do the drill core, it's actually just calcite vein. And on the surface, when the calcite, the oxides and the manganese come out, and the little bit of magnetite, little bit of pyrite in the vein gets oxides to iron oxide, and the manganese in the carbonate manganese. I have a question for you guys. How do you tell whether it's if it is black? How do you tell it's iron oxide or manganese oxide? Hey,
Scratch it.
yeah. See, your fault. It's said. Scratch it. If it is actually in red, it's iron oxide. If it is still black, manganese. So we are having a project for for examples of this, Antamina, so outside of your scar is the white marble, bleached marble. And with this vein, this one is diffusive. It's not a continuous mineral, but the veins are disseminated very fine grain, pure type, pyrite and galena. In those ones, there's tiny grains next to each other. So that's close to the Antamina, close to the crown, you got bleached marble, and you go further out, you see the veins are still the same mineralogy, but your bleached marble is much narrower. And if you go further out, the bleaching is almost done. But you still have this black vein that's fully bright and correct, and also again with that very fine grain. So again, that's the lunar pattern. This is the subtle feature outside of the scar itself. But when you see this, actually, if you see this on the surface, it's probably better, because if you see scar on the surface, part of it has been eroded away. And if you see this on the surface, you don't know erosion yet. And we can also use carbon oxygen isotopes to look at it. So this is our material in Honduras, and you see this is a shale. That's another shale. So the shale is parallel to the bedding, and those patterns, those are the skarns. So those patterns, those are the skarns. Some of the skarns are parallel to the shale. Those are the mantles. Some of them are cutting across the bedding, and here, and here, here. Those are the chimneys. Those are beautiful skarns. And so that's the geology setup, the background. Then if you do the because carbon and oxygen, that's carbonate, and you can analyze this. In the old days, may be difficult to analyze. Nowadays, it's $20 a sample. It's way, way cheaper than your rock analysis. And here, on each spot above, that's oxygen isotope accumulation. This one is carbon oxygen carbon isotope accumulation. So for the background of this, sedimentary for oxygen is 20 to 29 per mil normally. So if you see the number lower than 20 per mil, that's hydrothermal signature. So if you look at here, this sample got 25 per mil. So this is the original sedimentary signature. And you go here, 6, that's hydrothermal, 14, 4 and 4, 18 and 9 and 14. So those are all hydrothermal. So if you measure the distance, this one is about 300 to 400 meters away from the skarn itself. But watch out, this is just a massive limestone. If you have a fault, hello. If you have a fault, this goes at Mochito, it's 4 kilometers. And at Candelaria, we have had a master student, and this one goes to 5, 6 kilometers. Alarm fault depends on whether you have a fault or not. Alarm fault will go longer, much longer distance. So around Bingham is a PhD student currently working on that. It's about it depends. If you analyze whole rock, it's about 4 kilometers. If you analyze only the veins, you dig out the veins and send it for the carbon oxygen analysis, it goes out to 6.5 kilometers. So that gives the signature for the. At this distance, you don't see any garnet, no pyroxene, no wollastonite, so just carbonates. And if we can have the capacity to detect the distal signatures, and that makes exploration much easier. Okay, so that's the distal doning patterns. Okay, so that's the alteration doning pattern. We may also have a metal doning pattern. So the metal doning pattern, again, watch out for the metal doning pattern. It's not one zone after another. It actually have overlaps. There are always overlaps. What we are talking about the zoning is looking at the peak position. So that's the peak of moly, that's the peak of copper, that's the peak of zinc. So we're looking at the peak position. If you're only looking at everything, you always have overlaps of all sorts of metals. So for this one, you need to look at the hybrid. Look at the peak position. So if it is an oxide magma and relatively more not so mafic but moderate kind of maleic, we will have moly. If it is very mafic, then it turns to have very little moly. High moly always related to very caustic magma. And so the moly content, the peak is actually either inside the intrusion, like in Antamina, or right next to the intrusion in the skarn. And the copper peak actually is away from the intrusion for a short distance. And you go further out, that will be zinc peak, then the lead peak, then you go out for the silver peak. And here, some of the silver is 2,000, 3,000 gram per ton kind of grade. And then you go out, actually, manganese is even out. And manganese, alabandite in Uchuchagua, you get to a 30%, 40% manganese. Get that. And after that, it's typically out. And this part, so Uchuchagua is manganese in this part. Baya in Turkey actually has arsenic. Think of it. We run out of, so we go to particle skarn, diesel skarn, CRD. By this time, it's already CRD. Remember, we can even go to carbon type. And in carbon type, also. And the pyrite is arsenic pyrite, can turn up to 10% arsenic. It also augment and react. Why some of them is more manganese and some of them but you notice there's another kind of. Okay. So that's an example of Antamina. You see the moly high is in the middle, and copper is outside of the moly, and zinc is even outside of the smooth copper. And lead overlap with zinc, but slightly a little bit more. Like this part is outside of the zinc. So moly outside to copper, then to zinc. This one, this is Uchuchagua. And you see here, this one is zinc lead, it's high zinc lead, the red dots. And high silver is blue dots, high manganese is brown dots. The gold. Again, it's a cloud. But if you're looking for the major things, you can actually see that most of the red is here, then you can make a line here. Most of the blue is overlapped over there, but most of the intensive is part to make this. And the manganese is more outside. Gold is the yellow one. Gold goes no regular patterns, but still you see this one is showing the zoning pattern toward that direction. And well, happen to be here. This one is bunny zone. I checked the drill holes, and there's inner scar. Over there is no dikes, and here that's only narrow dike with inner scar, and outside is copper mineralization. The copper actually is not right next to the dike. It's slightly narrow scar zone, then you go to the CRD, get massive sulfide. Get high. The copper is not shown here yet because they are soon to the acid. And so beautiful zoning pattern from copper to zinc, silver, manganese. Okay, and so that's some examples with good zoning pattern. But actually, if you look at the whole picture, look at all the skarns, So this one is based on the compilation 2019. As I compiled the Skarns in China, there's about 390 Skarns in the database. China is an interesting situation. Is there originally they follow the Soviet Union pattern, so they are in a planned economy. And Western country, we will look at the metals. We say, oh, this one is likely make money. We will do the resource definition, copper and gold. If zinc lead is not likely to be mineralized, and we don't even do the calculation. In China, because it's planned economy, they calculate everything. And even if it's only 2 tons of gold, very little, they will do the calculation resource definition of that. And so it looks economically it's silly. But for research, this is a great example because you can do the comparison of all the metals. And so if we put everything together, that's the big paper, so summarize the metal zoning pattern. Actually, the zoning pattern is related to your magma. It's not one pattern, not a single pattern can explain everything. So we are looking for copper and gold. That's what we're looking for. But actually, there are other scenarios. So we have to have 4 scenarios to explain all the zoning patterns. One is oxidized and oxidized magma and relatively weak to moderate fractionation. That means it's relatively more mafic. So this one is more mafic. So this combination will be diorite, fourth diorite, dacite porphyry, that kind of combination. Well, if you have this kind of intrusion, and then inside the intrusion, you can have porphyry style alteration or indoskarn or both alteration. The metal is, it could be moly and or copper inside intrusion. Relatively small amount of moly. Then if you go to the proximal skarn, you will be mostly copper and or iron, and plus minus gold, plus minus moly. And if you go further out, and the distal one, you actually can have distal copper. We can have distal copper, then the zinc lead plus minus gold will be the far distal part outside. So that's scenario 1. And another scenario is you still have oxidized magma, but very strong fractionation, which means this will be granite. Well, if you have this kind of situation, inside the intrusion, you will have porphyry moly mineralization or Bryson type tungsten. Then you go out to proximal location, proximal skarn, massive, you get moly and or tungsten, plus minus iron, plus minus copper. Then you go distal, this time it's not zinc lead. Actually, it could be moly, could be tungsten, plus minus copper. So that's another scenario. A third scenario is you have reduced magma. You have reduced magma and strong fractionation. And this time, inside the intrusion is Grayson type tin. And tungsten can be related to oxide magma, can be related to reduced magma. It depends on what kind of metal together with it. If they together with moly, that's oxidized magma. If together with it is tin, reduced magma. And then you go out, that will be proximal tin mineralization in the proximal skarn. Then you go further out, you can have tin veins. And that tin veins, you go further out, it becomes zinc lead veins. Another scenario is reduced magma, but it's relatively more mafic. Inside the intrusion, we can have indoskarn gold. And that's Alimon, Morelos in Mexico. It's indoskarn is gold. And proximal skarn is also gold only, no other metals. And distal one, we can have zinc, lead, and gold. This one is not Morelos. Morelos haven't got to that distal. And this is Caijiaying in China. We only see this, haven't found those proximal. So that's the pattern. So we need to have 4 zoning patterns to explain all this. Well, at one location, you probably will be mostly one type of scenario, but watch out for differences. I work in Chile, Peru. That one got considered. I work exploring this part. So if the company wants to look for copper and gold, spend no matter how much money you spend, disappointed. You go proximal, you get more and more cheap. So that. And if you look at this, you will notice something. The gold is actually very versatile. It can be proximal, it can be distal, even in CRD deposits. Beiyang in China and outside the Skarn, it's a CRD. It's mostly siderite and galena and with gold. And so it can be proximal, it can be distal. It can be related to oxide magma, it can be related to reduced magma. So gold only is related to reduced magma. And gold with copper and not oxide.
Is that because gold forms different complexes?
Yeah, exactly. Yeah. So if it is reduced condition, gold is transported by bisulfite, and that's reduced. And if it is oxidized and high salinity, it can be transported by chloride. And so that's why we can do different scenarios. And another kind of feature is, or you don't notice, is the gold we're mining at very low grade because we need more gold, but you have more metallurgy method, so we're mining more lower grade gold. If we mine lower grade copper, if we just mine 0.05% copper, then the reduced magma will also have some copper. And you also notice some metals, they don't occur in the same system. So tin and gold almost never occur in the same system. And tin and moly, again, not really occur together. Gold and moly, unless you have copper, you have porphyry, copper, gold, moly together, that's okay. But you don't have a porphyry, gold, and moly deposit. The two, just by themselves, they don't occur. And that's one. And
in the examples we have in the porphyry zone,
yeah,
gold and moly.
You have copper often?
Yes.
So that's the scenario of gold, copper, and moly together. That's okay. But only gold and moly don't occur together. And it's the same thing as the porphyry deposits. If you have gone to David Cook's porphyry seminar, and you will see a diagram shows a porphyry deposits. Oh, and if you go to the porphyry deposit metals, you will see this diagram. So gold here, copper here, moly here. You have all sorts of clouds here, here, and here in the middle, but nothing on this one. Same thing for porphyry copper. Essentially, the magma part, porphyry and skarn are the same. The fluids and the metals and redox and everything is the same. The only thing skarn different is water. So could be the same feature for porphyry. Okay. The only thing also is carbonates are much more reactive than the volcanic rocks. So skarns have many more metals than porphyry. Okay, and also what magnetite is abundant in many types of skarns, even in thin skarns, which is reduced in Sweden. And so magnetite is moderate. It's not particularly oxide. It's not particularly reduced. Remember, magnetite is iron O and Fe. 203. So you get both oxide species. So hematite is indicative of good oxide, but magnetite not. You may think, oh, magnetite got to be oxide. Actually, not good.
So, one question. Which is the big behavior of silver?
Silver is more distal.
In some porphyry around the batholith, the batholith is in the center part.
Well, what out whether the battery is a causative intrusion or it's just a host part. A lot of times, the older intrusion could be a host part. And we'll mention that. I will just mention that the Colorado in Mexico, you have intrusion, more intrusion, I guess. Right now, it's a very small interval. And then you have Skarns here and CRD here. And now you run out of your limestone, it becomes volcanic. The CRD, when it's closer to the skarn, is massive. So massive CRD closer to the skarn. And then you go out, become vein type CRD. And that vein extends into this. That's your intermediate epithermal IS veins. What do they mine for? They're mining that for silver. Because that's the distal part of the skarn system. Even it's inside the volcanic or intrusive rock. You mentioned the batholiths. If it is the batholiths, the mineralized part of the batholiths already usually weak. So the batholith itself, there's no way the batholiths can generate mineralization. It has to come out from somewhere else. Like this scenario, it's hosted in volcanic rocks, but the source of that silver is way down the road. So if you have that situation, think about trying to look for the source. You may have more metals. The Colorado mined for about 20 or 30 years for these epithermal veins. And whole story, you running out of resources, you start to panic and you drill everywhere. And they drill deep holes down there and not going to find a big star. Way bigger than the epithermal vein we have mined for 20 years. Okay. Some example, or again, the ramifications of those zoning pattern, say, zinc lead being distal is well known. And well, some people will say, oh, if I follow it up, I will find my copper. So will you find your copper follow up by zinc lead? Watch out, zinc lead can be related to both, to be oxide magma or reduced magma. So this is Gerdio in China. So zinc lead veins, distal is shallow part, then you go closer, it becomes thin and zinc lead. And eventually you go to the closer part, is mostly thin. And how much this deposit has? Well, this is the district cyber center, 3 million tons of tin. So for relative to copper, 3 million tons, it doesn't mean much. It's not really big, but tin is much less than in terms of copper in the cluster abundance. Queensland, Northeast Queensland, has been used to be a major production area of Australia or the world. The whole area, it's a few thousand square kilometers. It's a major production district. Do you know how much tin is there? 0.2 million tons. That's the whole district. And this single one, 3 million. Huge. Okay, so zinc lead, you have to think about the situation, whether you get the tin or you get the copper. Another point is that zinc lead being distal is well known, but actually other metal can be also distal. So this one is a tungsten skarn. This is a plan map. This is cross section, and cross section again. You see, this is limestone here. This is shale here. the ore body you see as close to the curve, close to the boundary. That's one of the examples. But if you look at skarn, there's so many examples that the skarns occur at the boundary between limestone or shale, limestone curve, limestone and basalt. And so this part tends to be slip faults, and it's a high permeability. That's why we have more permeability. That's one point. Another point is if you look at the plan map, no interference around. This one got to be a diesel, and they haven't found the interference yet. The diesel skarn is tungsten. Another example, even more interesting, and this one, 2D in China, again, 2.7 million tons tungsten. One deposit. This is not even a several centers, one center. Queensland and also Australia, some Western Australia, like Oklahoma, that big tungsten skarn. Those ones are 0. Forget the whole district is 0.3 million. It's single deposit. If you look at the geology here, this is the dike. Well, small intrusion, it terminates before it reaches the surface. So it's a small intrusion, and the pink color is the tungsten ore body, and the green part is the copper ore body. So you look at around the intrusion, it's mostly copper and tungsten. So you go further out there, again, you still have tungsten and copper, but you go to the closer to the surface from here around, you only have copper. So this time, copper veins is the distal signature of a pig. They were mining little small pits on the surface, mining for the copper. And eventually they drilled deeper and found the big. Again, for the tungsten, in the old story, traditionally the tungsten skarn, a lot of theory out of North America, Canada and USA. And it used to be saying tungsten also related to big batteries. And it turned out this example changed the understanding of that. And over there in North America, in California, in Alaska, those tungsten skarns, they're thinking they are big, but compared with this one, they're way smaller. And if you look at this, very big tungsten is still related to the shadow. So probably over there in California, the bigger part of the tungsten is rooted away. You don't see the shadow part, and you only have a smaller amount. So this one actually tungsten also related to more intrusion, similar to copper.
Okay, so can I ask questions, Zhaoshan? So can we turn the question around?
Yeah.
Say we know there's a copper deposit. Yeah. Chalcobamba. So does that mean there will be a zinc lead deposit somewhere around?
Oh, that's another topic. Will be the fertility of skarns. We do fluid inclusion analysis, and we can tell. Well, we did only 3 examples, but it shows difference. If the skarn is only zinc lead, no copper, the fluid inclusion in the person, low copper, very low copper and high zinc lead. And the one with copper and zinc and lead, actually in the fluid also high copper and zinc and lead. So it can be sure because the magma actually is somehow some magma is rich in certain elements and some of them are not. Yeah, it depends on, to be more certain than.
Okay, and then also the deposit needs a transport and a trap.
Yeah.
It's possible that the fluids are just, evenly dispersed out into the water lots and they're not actually concentrated in any way. So all of that zinc and lead is there, but it's just very widely dispersed and is not concentrated into the deposit. So I guess
That's a possibility. If the wall rocks are siliciclastic or volcanic rocks, that's typically the pattern. They get dispersed. But we're in a carbonate area, this is a very good trap for if there's metals. This trap has a very high chance of.
they do need to be focused.
It will be focused. And there are good ways of focusing on the next slide. Okay. And this skill we also mentioned that not to repeat anymore. So just what else? The CRT also a zoning pattern closer to here, more massive, and if so, there will be many patterns. Okay. And now, want to take a break?
What's that? How much more do you have?
We can finish earlier with the important ones.
Yeah.
I need to use the toilet.
Yeah. It's looking at go through the west. We say, it means something. Yeah. Yeah, it is such a motivation.